Click. So that's a general overview of the deposition screen. The process screen, you have the same graph, just looks a little bit different. And you have the matrix. For probably the next year or so, you'll only be doing an A/B process. You may get into, like if you were doing hafnium, you could do TMA H2O, hafnium H2O. So you could have a 4x2 or even a 4x4 recipe for later on. This is our standard matrix that you could expand into over time, depending on what options you have. For the most part, you're just going to be using this area right here. Just like we did with the water and the TMA. You have the process phase. This, you can look at these as lines. Process phase, ALD gas flow mode, and ALD heater mode. These are set as lines in a recipe and populated in this information box. Finish ALD layer, it's redundant as the other screen. You can clear reactant definitions. So if somebody stopped the recipe in a not nice way, they just stopped it from the recipe monitor instead of allowing it complete. You may have a situation where the reactants have been left populated in a matrix. So you run a recipe on top of that, it's going to stop at that point. You might have to hit clear AL or clear reactant definitions to clear that screen. General user heating screen. So you have enable heaters, off all heaters, and reset all over temps. If you wanted to do this manually, you could do it here. The recipe tells it to do it, so you don't have to do it manually.
Please continue on the heating screen.
It's good to check, but you don't have to do this. These are commands that are already called up in a recipe. The substrate heater functions, that's this section right here. The control for the substrate heater is different than the control for your line heaters and your process chamber heaters. So, and this is still all controlled through the recipe. But if you go, you can turn it on and off manually if you wanted to. You could give it a set point and control it manually. Most of the time it's controlled through temperature control, so you have a ramp and a heater set point. That's actually the preferred way to run this. Tuning, you won't be doing any tuning, but this is where if you wanted to play around with the PID values, you could do it here. And if you wanted to put a different over temp set point, you could change that here. On this heater screen, you have enable. Enabled means the command was received, and you have a temp set point. You're only showing one TC, one of the two TCs on the screen. This would be the control temp. Your output set point is just what the percent output is giving to the heater relays, how hard they're driving. Heater definitions, we've already covered those. Error, if one of the heaters go out or it over temps, you'll get an error and it'll automatically shut off. This 6553 is the default 65535. So if you have a thermocouple that's unplugged or one that goes bad, sometimes they do go bad, it'll read 65535. If there's a difference between a control and over temp thermocouple or TC1 and TC2, you'll get an error. If you over temp, you'll get an error. There's different things that cause errors. To clear it, you just reset all over temps. And a maintenance screen. Under system info, you have recipe logs, events and other logs. This is where you could actually come in and your archive is under here. So if somebody did something and they went up and they cleared acknowledge, I said, I didn't do nothing. No, this gets recorded all the time. You can come into the events and open it up and figure out what happened through here. That gets recorded and backed up every 24 hours.
Where is that?
Under maintenance, system info. Some things were put into the software, but they're not incorporated 100% yet. One of them, system drawings. So you won't have any system drawings. It's set up for things that will happen in the future with the software. If you want to disable the interlocks, you can disable interlocks from here. Not recommended, but sometimes you need to do that for troubleshooting. So just be aware that disable interlocks are here. If you want to back up the controller, maybe you have a lot of critical recipes after, say, 3 months or 6 months or a year, you could back up, do a backup, and it'll save all the recipes and other inputs. But you can back it up. Generate support file. I have no idea what that is. I'd have to look in the manual. Some values, you can scroll down here on a scroll bar. I never use this. If I'm coming into this screen under this tab, I'm usually disabling interlocks, or I'm digging into events and other logs. System signal tab, you can come in your analog string outputs, inputs, discrete outputs, discrete inputs are here. This is more information under the maintenance than you see under like operation. Maintenance, just a lot more information. You can come in, you can scroll down, depending on if it's an output or an input. You can set the output, you can monitor the input, come in. Discrete outputs, if you push any of these, it's the same as pushing a button on other screens. However, there's operations that you could do from here that are not buttons on other screens. Again, just a lot more operations from here. This is something that not everybody should be getting into. You can scroll down and you can see the different names. And as I said before, if you bring the cursor over something, you can see exactly what the signal is named as. It's not always intuitive. Sometimes they're just a little bit different. Mostly if you're looking for that signal name in regards to charts or signal recording, you might want to hover. I want to record this. I don't know what it is. So it'll give you what the signal name is actually. And then you can go in a pull down menu and put it on a chart or put it into the recording. The discrete input is just exactly what it is. It's an input. So it's a 1 or a 0. This section here, you won't touch it. Software manipulates this part of it. Interlocks, these are all the interlocks, the software interlocks that are tied to this system. Not going to go through every single one of them. If you want to, you can kind of click on them. You can come in here and you could say, here.
We don't usually need to.
You should not. There's reasons for it. We might disable some like if we're troubleshooting, but there's a purpose why they're here. Now, like we've had a couple interlocks before come up with the yellow. It's much easier to double click on that and it'll bring you to the exact interlock. There's both behaviors and interlocks. The difference between a behavior and an interlock, a behavior automatically happens. So we manipulate it. So if this is a condition to automatically do that. With a behavior, you won't get any prompt. The interlocks are set to give you a prompt. And even though that condition might clear, that'll stay up here until you acknowledge it. Let me come back here. No, I'll explain that better in the recipes. So system users. I don't know how this university is set up. Some universities, they work with outside contractors. They'll train somebody on a tool. Maybe they're just doing research on run recipe. I don't know if you're planning to do that or.
So now I think we did.
Okay. The users that are on here,
Simple user.
you have two. You have KGLC and admin. I would keep both of these. Yeah. Something here. I'm changing it, saving it also. So if you wanted to have individual settings, so everybody or maybe certain specific people only have access, you could put their own username and you could set them up with a little bit of an account here. And the buttons will determine what they have, what they're allowed to do. So you have some control over here. You know, whether you want them to be able to edit recipes or see other peers at the same level. So if they're at a technical level or technician level, they can see other technician level recipes. So this just sets up what you allow them to do. On here, there's something called button configuration. The button configuration sets what buttons you have all around. So you can change it. You can have different button configurations. Maybe some people, you want to have a button configuration where the recipe editor isn't even on here, or the maintenance and UI configuration has disappeared. Admin and KGLC is set up as super users. They have access to everything. But you can control what the individual operators have access to. This is covered pretty well in a manual. If you want to experiment with that, you can come in and create a fictitious user and change what the permissions are, and then go back and see, oh, okay, they can't see this or they can't do that. That's really the best way to learn if you want to do that.
We are just gonna be of us using it, so it shouldn't be I don't think we need it at this time. I don't know.
Yeah, the option's there if you choose to in the future. And that's with both of these systems. Everything I'm covering right here is redundant on both of those.
It's more complex than everyone. It's like can work with that without any coordination.
Yeah, well, the software set up for some universities, they might have 50 users.
Yes.
And that's,
Yeah.
you know,
Exactly.
that's 500 of these. You can get a lot of trouble with that. So they set it up. Okay, they limit to how much different users can, what they have access to and what they can control. Email setup. The last I know, this wasn't set up to automatically put, so I think this is just nested in the software for future use. Heater setup. You may come into here. This gives you a whole lot more information than what operation
Maintenance.
heating. So you only have a little bit here. This maintenance
Maintenance.
heater setup, you have both your thermocouples reading. you have a ramp option if you want to control it for your system heaters, along with your substrate heater. The enabled and enabled are both redundant.
So this one is the click button. This one is indicator.
True.
These are all inputs.
Yeah, now you can input the temperature on
Based on
operation. You can't input a ramp if you're doing it manually. The recipe does everything the way it's set up right now. If you want to change something and do a manual operation, you could do it from here if you want to do a ramp rate. You can't put a ramp rate in from the operation screen. You can,
Here you can.
yes, if you're doing it manually. There's a position in the recipe where you can put a ramp rate, so the recipe automatically populates it. Some people maybe don't want to give them all this information. Also, if for some reason you're only using one thermocouple and you don't have two, maybe one went bad and you only have one and you order some more thermocouples, you can disable the second overtime. So you can disable,
Where's the second?
here's the,
Second.
yeah. So on this channel right here, the ampule heater, there's nothing plugged into TC1.
Yeah.
There's nothing plugged into TC2.
Why the arrow? Why the arrow is highlight?
Yeah. So there's an error there. Whenever we go into doing a little bit of training with the ampule heater, we'll actually create errors by plugging the thermocouple in and out. So if we unplug one of these thermocouples, okay, so I'll give you an example right now. So this source one valve heater, if I were to say a thermocouple broke, right now, might want to look at the screen while I disconnect it. I'll reconnect it. Okay, I replaced the failed thermocouple. So I can come into here. Yes, it reset and it'll reset it. Yep. If I want to start it again, it's already up to temperature, so I'll just punch in the same value. I don't have to worry about a ramp. It didn't lose any temperature. So this is your overtip set point. Sometimes this matters. So for in the case of zirconium, you heat it up to 75 degrees C. You don't want to overshoot because you don't want to thermally decompose it. So in that case, you might want to put the over temperature at 80, just so you don't have an overshoot. On here, there's PID zones that you could call up. Most of them have a name that corresponds to that heater that's already set. These are the PID values, and this is what's populated.
Don't need to find them.
You won't have to change them. They're already set to tune. If we get into real weird temperatures, you might change that a little bit. You have some of the same inputs that you did on the other screen. There's actually something here on this screen as a PID table. You can bring the PID table up. And from here, you can input your PID values. In this case, you save and export to controller. These values are held in the controller. They're not held in the computer. Your interlocks, those values are held in the controller. Recipes are held in this computer. So whenever you hit run recipe, once that recipe is pushed down in the controller, then the computer is just used for information, for feedback. You can unplug the computer and this will still run its process. Also in the PID table, you could limit the output. So you could, what the max output of the heater range is. So you can limit the 20, this is in percent. you can limit to 25% output. On your ampule heaters, if you choose to, we have ampule heating recipes. You'll have two different PID values. You have a heater ramp with no I, no integral, and you'll have a steady state, which has an integral. So whenever we're running an ampule heater recipe, not the normal heating recipes, on ampule heating recipes, so if we were heating up zirconium to 75 degrees C, the recipe will say set point 75 degrees, input heater ramp, no I value. So that'll be almost linear whenever it's coming up if you look at it on a graph. Whenever the recipe will state whenever it hits 70 degrees, shut off the heater, put in the different PID values, the steady state, which incorporates I, and then it'll go from 70 to 75 with the incorporation of the I. What this does, it prevents integral windup, so you don't have that overshoot. The last time, actually, I just did this like 2-3 weeks ago, and running the recipe on zirconium with these PID values, the overshoot from 75 degrees C was 0.65 degrees. And then the undershoot after it was like 0.15 degrees, but still within 1 degree. You're not going to thermally decompose that material. That's how you want that to run. So in regards to the ampule heating, that's the reason why you have two different sets of PID values. And then we just have this as a ceiling acting as a buffer. You can input any PID values you want, but this is set up for normal operation, what most people will use. More so you're aware that it's there. If you get into running something other than hafnium or zirconium, then maybe we might change the PID values, or we could go ahead and tell you to wrap the heater on an empty ampule, water ampule, maybe not that exact precursor, and then we'll run the temperature up to whatever we think should happen, and then we can run a tuning program to go ahead and tune for those PID values, which is a different set of software. Then we can have the new PID values and put it into this table, then you'll have it. You won't be using that in the near term. Maybe future use, but this will work just fine for what you have. Just so you're aware of where it's at. And these are redundant as before.
Based on your recipe, to change those PID values, you can just come here and adjust it. You do recall any recipe you have encountered required to change those PID values?
If, for example, University of Minnesota was running cobalt, so the PID values were a little bit different. Okay. So we just created, we could add lines. So we could copy the PID values for the ampule for 3A, and then we can change that to different PID values that corresponding to a different temperature.
Okay, so with that value work on this machine, or you
Yep. Yeah, it will work. The same software. Mm-hmm.
So this set point temperature for heaters, this set point temperature are typical values which may work for a range of recipe, majority of recipe, or so specifically should be entered for any recipe, any new recipe.
This is more set up to what your substrate temperature, what temperature your substrate will tolerate. So this heating recipe is set up for aluminum oxide running at 332 degrees, assuming you're going to do wafer pieces or wafers themselves. We might have to set up a different heating recipe if your substrate won't tolerate that. Maybe you might need a heating recipe for 150 degrees. That's fine. We have them. You could create them, or it would be much simpler just to ask it for it until you become more familiar with the system.
Ask you a question. So to run a recipe, So in this system, approximately how many inputs we need to consider to insert. For example, this is a new recipe. This is heating recipe. So we need to input several.
Recipe itself has a temperature.
Yeah, I think that answer will become clear whenever we get into the recipes themselves.
But my point, I got you. My point is that if we want to develop the recipe, so we need to consider all of these inputs. For heating input, then there, I mean, many.
If it's brand new, you don't have any existing recipe, you have to put it on.
Exactly. Not existing, a new, if you want to develop a
If
new.
I have a recipe for this particular material, then we have to have this value.
We already have them, just ask it for them.
That is something you've never been dealt with. So the new material,
New coating.
new procedure.
New precursor? It may or may not change. The temperature is usually more dependent on what the substrate can tolerate, more so than what the precursor can do. This is heating with the reactor in a system. Precursor heating by itself is just one of the heaters if you wanted to heat it.
So what I can perceive is that, so this heating recipe, as long as you are using the same substrate, is almost the same. You don't need to change it for heating recipe.
Yeah, as long as the heat, for in this case, as long as your substrate can handle 300 degrees, 332 degrees, you can run this.
I understand, regardless of the material you are putting. But just based on,
Okay.
It may matter because you don't want to have your reactor and your lines so hot that you're going to decompose the precursor material before it gets to the substrate. So you may have be running a precursor that requires these temperatures to be a little bit lower. Not always. Sometimes.
So right now, the silicon wafer is at 330 degrees. Because it said the wafer can handle that.
Mhm.
What if we run it at a lower temperature? What will happen?
If you run it at a lower temperature, then your growth per cycle will change and will shift a little bit. And the possibility of
condensation.
having, well, if everything's heated, you don't have the condensation. But you might have to add a little bit more time to your purge to clear out the material.
So the reason you 330 for the growth rate or deposition rate to be optimal for this material.
That's what's optimum. There's a whole lot of history on aluminum oxide at that temperature. You know, we know exactly what we should be getting at that temperature. So that's the reason why the parameters.
So in other words, that if we're going to deposit a new material on a silicon wafer, then we have no idea what temperature will be good for that. So we pretty much can start with
Keep the same.
this temperature and see how it grows, and then
I wouldn't do that. I would get in contact with myself or Nolan Bruce, say, I seen this technical paper, I seen this white paper on a material. Can we run it on this tool? And if we do, what parameters or what process do we need to change to be able to do that? You have 30 years of knowledge available to you. Why would you want to reinvent the wheel? Just ask us.
Yeah, these are all
This way, you don't spend $2,000 on a precursor and end up ruining it on the learning curve. Just ask. Chances are we've already have had that recipe, have an idea where to run that recipe, or at least are aware that there's maybe a new precursor that's came about. I would not I would not try to learn that on your own. And this is something I would tell everybody, not just you guys. Why? You have the resource of a research scientist that's all he does. He lives for it. Actually, two now, because we have two research scientists up at Penn State. That's what they do. Bruce designs it. Tom runs the experiments, and that's how we're built right now. So, yeah, if the resource is there, use it. Absolutely. Just ask us. You know, I want to, can we, and sometimes you might not be able to run something. We would tell you that too. But if you can do it, and sometimes customers say, well, I want to run this material. We don't have any recipes. We don't have any experience with it. We'll give you some benchmarks. So it's an advantage to us to work in a collaboration with universities and other users, because this way the learning curve is very steep. The chance of success is a little bit greater. You utilize our resources and we work with you so we have a little bit better idea of what's happening. It's a win-win situation for both. And there's universities that we have a collaboration agreement with for just running experiments to work with, to use our resource, our knowledge, and we get information from their experiments.
So those you're talking about, is that something we have to pay for contract, service contract, or something like?
That's different from a service contract. So, and that type of collaboration is for research. It's not like something you have to sign up so you have access to a library of information.
Yeah. I think my question is, let's say 1 year later, we have some question, have some new things we don't know. We reach out to you. Is that
Just send an
so
email.
we don't need any service contract for you to provide information?
No, we don't work like that. We spend a lot of time with the customers. And a lot of that cost that falls on the company. Some companies are like, well, you have to have a contract to talk to us, you know, after whatever period of time. With the ALD group, different from the PVD. And customers say, well, your system's broke. Then we have to dig into it and find out maybe it was something that the customer was doing that they weren't aware of. So it's advantageous for us to work with the customer for their success. Because this way you can run it and say, well, you run it the way you thought would, maybe that'll damage the valve in a way that you weren't even aware of. Now, not only did you kill the precursor, you killed the valve. You're at $4,000. Or worse yet, maybe you damage the system and the lead time for the parts now 36 weeks. You don't want that either. Just work with us. The Kurt Lesker company is really good at that in general. The ALD group is very good at that. Plus, there may be sometimes I come down to this area a couple of times a year. So if I'm have a short visit or install someplace else, I might just say, hey, I'm going to be in the area, and I'll probably do this because you guys are just learning this. In 6 months or a year, if I'm coming through here, I'll say, you want me to stop by and answer any questions? Because you won't have all the questions. Yeah, the more you use it, the more questions will pop up. I try to pull out as many questions as I can while I'm here, but it's not going to be all of them. But yeah, the company, and especially the ALD group, it doesn't work like, okay, the system signed off, you're done. Okay, we're not talking to you unless you pay more money. The company isn't like that. It's very good. And the amount of time that I spend personally with customers after the sale is it's many hours. But it works, and it's a good relation with the customer, because whenever you want to have an upgrade or you want to put an oven in, it may cost $10,000 or $20,000. Then you have some degree of confidence. There's a relationship. This is going to work. It's just better in the long run. It pays dividends. Sometimes it's a little bit costly up front. I know you guys are new at both of these, and you're going to have a lot of questions. The more we can help you understand, the better you're going to be at running the tools, the better your results are going to be. Then you understand the capabilities and limitations. Now you can start to design your own stuff as you work for funding. You can say, yeah, I can do this, or yeah, I can't do that. And it helps funding, especially with university, helping funding, help buy upgrades and tools. So it's just better long term.
Had a lot of people outside visiting the past a couple of months. So, you know, every time they come here, they say, you know, your name, your brand, you know, it's also a good thing for them to.
Well, that happens a lot of times with grad students and stuff. They'll move on and they'll go to other companies or other universities or whatever. And sometimes, depending on the contract, they'll take the tool with them. It depends on what the contract is with the university. We had one gentleman that he took the tool to 2 universities, and he moving to another university, and he had the option to take the tool with him, but the university worked out something they're going to buy the tool. He went to this new university, and he's going to buy a new tool.
Here's this model. I like it.
Yeah, it's worked out. It really has. The MFC setup in the maintenance screen, you could set it to run different gases. You're going to only run argon or nitrogen, so you can change it here.
So right now, argon. So,
Yep. The only place you run nitrogen at all is right in the 4 line here. Process uses all argon. System logbook, you can look in the manual for this. I don't think it's totally incorporated yet. UI configuration. This is the button. This is where you can manipulate the buttons. So it has the navigation buttons. The navigation buttons are here.
I don't even need to do too much for me.
You don't have to do any of this because it all looks the same. If you're just using admin, but this is where maybe I was having a user, I didn't want them to see this, then you can come in and create a new configuration, and then you can change what can be seen on different buttons. So this is the button configuration is where you can go ahead and change how the screen looks and what operation. So you have create user where you can limit some of their operations. This is what they can see and not see. You can also, and this is default because that's the only button configuration it has. You have the recipes here that are pushed on this side. So the command, the very most common recipes, you could just have them hitting a button here. So if you had an experiment you're going to run 40 times for like a design of experiments or something like that, you might not want to have somebody come in and running the recipes where you have variables. You want to just simple, run this recipe, run this recipe. So in that case, you can have a recipe as a button. They're just hitting the same thing all the time. So this is where you create that. So you could say what the button name is, that could be anything. And then what the recipe is. This is space and case sensitive. So you could have, say, the button name sample recipe. And then the recipe itself, I would click on a recipe and copy the name and paste it in here. This way, you don't have any case or space problems. And the manual covers these pretty decently. Configure values, you won't use that. Source tabs, software sets this up, you won't be here. Signal editor, you won't be here either. Software sets it up. Recipe operations, software sets that up too. So you won't have to worry about that. Operation, this is where you're going to be at almost all the time. Maintenance, you may be here for troubleshooting, and you may get in the heater setup. The heater setup also has a tab that says error setup. This is set up from the factory. So if there's, it'll monitor both thermocouples, and if one drifts too far out, it'll cause that error. So some of this is where errors are. If we're working with you or with the recipe, if anything needs to be tweaked here, we'll go ahead and set it up that way. You won't be here without, you really shouldn't be here unless, we're working with you. This host utility down here on the toolbar, this drops down on the toolbar anytime you launch a software. You can't close it. It actually works in conjunction. On here, there's a cheats tab that you should be aware of. And there's editors such as Calm. You can sometimes, whenever you boot up, the communication might not be 100%. We can come in and say, well, hit Calm and then save and exit. And it re-inputs that to the computer.
So open the software, this may not work.
It should. Sometimes we have a little glitch that comes up.
How do you tell you, please?
For example, if you have an analog input that isn't responding like it normally should, everything else is working except one.
Okay, so you click this.
Yeah. For now, just be aware of it. If we end up doing any troubleshooting remotely, you might see somebody come into the host controller and then change something here. Just so you're aware that this gets nested in the back. Cheats tab is the only area where anybody would be doing anything. If there's things that need to be changed to editing, you're going to see us do it remotely anyway. The more you see that operation, the more you're going to understand and be familiar with it. Takeaway just right now is just, be aware of it. So that covers the screen, the buttons down here. I'm going to go ahead and acknowledge this right now. So what's next is getting into the recipe editor.
I assume you already checked the temp.
Nope.
Don't know whether it was deposited.
I deposited.
Okay.
So if you want to, you can, let's take a break, like 10 minutes. So you can, I don't know if you want to keep this running or you can stop it and we can start it. Then we'll go into the recipe editor.
You mean recording?
No, stop recording. I just stopped it.
No, I stopped sharing. You didn't stop recording.
Oh, they stopped recording.
I think we cannot change it. They have to go over there. Anyway, it's fine. It's fine. I'm still gonna share. That's fine. It's leave it.
Oh.
Yeah. You want recording the cloud. Recording, you have to control from. Yes.
Oh, he is.
Okay.
Post.
Can I move this?
Yeah.
Yeah,
Okay,
okay. I want to do something before, I want to look at something here.
We take a break.
10 minutes break.
Yeah, we'll take a 10-minute break.
No more experiments in the summer. I haven't got a chance since it was installed. We had a couple of events. I couldn't really use it.
Yeah, and if I'm in this area and I have a couple hours or half a day or something like that, I'll stop in and just, it if I'm in the area a lot of times, especially with new users, how you guys doing? What questions you have? It pays dividends later on. We don't want to leave you hanging.
Thank you. This interface is not simple. I don't remember what we. Twenty coffee?
Coffee? Yeah, if you have coffee. Yeah, that makes better. Yeah, we'll get into the recipe structure. It's a lot to talk about. And then after I cover the recipe structure, that's whenever I'll step back away from the system and then it'll be more hands-on. And the more hands-on, that always generates questions. And that's where we want to be. How are you going to operate it? This way, if there's a question or an accident that pops up, we can address it. You have it like real time.
Resume?
Resume. No problem.
So he is the professor in charge of the lab. Dr. Shu, you know him?
Yes, I know him now.
Yeah, he's the one.
Okay.
Me and Dr. Kavir are postdoc here under him.
Okay. He's very attentive.
Huh?
He's very attentive. That's good. I like that.
He is gonna
So
be here.
he's the one that bought the system.
Yes, he's gonna be here as long as maybe whatever he wants. So he has to know and learn everything thoroughly.
Yeah.
Because he is going to guide a lot of maybe master's, PhD, undergraduate students.
Mm-hmm. Well, I'll be back through this area. Like, for example, probably within 2 months, I got a trip that I got to go down southern part of DC into Virginia for ARL, and I got to do an upgrade there. It shouldn't take very long, maybe a day or two. So in those cases, that might be an opportunity.
For you
If I'm
to
coming
hear
back through, depending on my finish. Hey, I'm coming through. Is there any
Sure.
questions you might have?
please.
And that doesn't mean you'll have to be obligated for that. It's just an opportunity.
Yeah, of course.
You know, and the more you use the tools, the more,
Question we will have.
and the more acclimated you'll get in running. Or why does this do this? Or why does that do this? Or can we? More comfortable you get, like, oh, can I do this? Or can I do that? And there's a lot of
Are you starting?
Not yet. As soon as we start, I will do a resume.
Okay. And let me know that I can start there.
At 3:30? All right.
We'll go for probably 40 minutes, 45 minutes for this part. Then we'll just take a break for lunch and then come back and run.
Okay. So you never get started, or you want to wait for people to start?
We expect you guys to come. If not,
Well, I'm recording, so.
yeah. It's gonna start.
Okay, we're gonna start. We'll
Yeah.
start. You good? Okay. Here. Move this down here. Recipes. You can come in a recipe editor. It'll show you the recipes. This looks a little bit different than before because I gave you access to see everything. So here's the individual. So this is the individual recipes. Some of them are abort recipes, just they're designated as abort recipes. Some have just PC pump, PC vent. PR is a process recipe.
PC4.
PC is process chamber. Okay, you have setup recipes and sub recipes. So that's the abbreviation in front of it. For right now, we're going to look at, since we need to retrieve that sample, we're going to look at the PC vent recipe. So you can come into here. Let me do an overall of this screen. So you can create new recipe, duplicate, delete recipe. You don't want to delete any recipes. I wouldn't recommend it. Some of the screens you might have where you can filter by signal or by category if you want to. So the interlocks are set up the same way. you only have a small amount of recipes, so you could see everything on the one screen. If you had maybe 100 or 200 recipes, maybe you would start to filter via signals or categories. But that's just your option here. You can have the ability to import and export recipes if you want to. You can run a recipe right from here if you wanted to versus here, or the recipe editor. Flatten recipe, don't worry about that. The preview steps, I can come into PC event recipe, or I can just select it over here. And this gives the steps of the recipe. Also, whenever you come in a recipe monitor, if you want to show progress, this is what comes up here. Yeah. So you'll actually see this in real time. Recipe calls and called by. This is if you have sub recipes in there. You won't really use it, but for example, the process recipe, this has sub recipes in it. So you might see something populated here. So on the columns, you have the name, view recipe, you can click on it. You can hit edit disable or include and run list. Edit disable gives it, you have to, so how do I put it? If I go into this recipe, I would have to uncheck this before I could do any editing. So this just gives you a little bit of a safety step that somebody deliberately has to take action on to edit a recipe. You don't have to have this checked, but it's not a bad thing to have it checked if you don't want somebody to accidentally change it.
This is under category of process.
This is under recipe editor. These are all your recipes.
Oh,
Has nothing to do with these. It's just this recipe
yeah,
editor. As long as you have recipe editor in this column, you can get to here. This include and run list. A lot of these recipes you might not want to populate in your run recipe. This pop-up window. So anything that has an include and run list checkbox
Find it here.
is here. Yes. Description of the recipe, you have a column in here for that. Security level, if you want to set up different security levels of what level somebody can access something, you could change it here. You could keep everything super user, or this is where you get into universities that have a lot of users. Maybe you don't want them to look at or mess with doppel level recipes. So they can only see maybe their own recipes or peer. You limit the peer viewing. So that's what this security level comes down to. Owner, you can put what you want there. Category, you could set the category. And this automatically populates here. So on the recipe itself, this screen, you have a lot of the same operations, but they're in a different position. So you have the name here instead of being in a column. And if you wanted to put a description, you could put a description. You could set the category and the security level. And you could also, do I want to put do I want to disable the edit? Do I want it in the run list? Same things you could do on other screens, just different position. This gives all your steps. So whenever we hit PC event, which we'll be hitting very shortly, the first step is it sets an abort recipe. Abort recipe, it sets as abort PC event. So if something were to go astray, what do we want it to do? Then we put a pause step in here, which you can do saying, do you want the operator to do something? Do you want them to check something? So that's this pause step, which we'll see. Then the third step, it asks if the pump is enabled. There's nothing in this column. Sometimes what's in this column matters. Notes, any notes that you want to put in a recipe, you can put under this note section. It doesn't impact the recipe at all. So sometimes whenever you're running a new recipe, you might want to put, check this step after running so many times or something like that.
PC vent, this is recipe for PC vent,
Yes.
and
That-
then PC pump.
No. That's the category.
So right
Go
now,
back to return list.
okay.
Yep. Click it again. These are all the recipes. If you want to see the recipes,
Yes.
you click on view recipe of that recipe. If you click on that box right there, that'll take you to where we were at.
Yes. And could you please let me know, I'm a little bit confused about PC vent and PC pump. What is this?
Vent allows you to retrieve the sample. Pump puts it back under vacuum. So one brings it to atmosphere, other one pulls it back to vacuum,
Right.
which we'll cover PC pump, PC vent, and the process recipe. I don't have to go through every recipe because once you understand the steps of those, you can understand the rest of the recipes.
Yeah.
On the recipes coming into this column here, skip. If we wanted to skip steps, we could select skip. And that'll just, it just jumps to the next sequence. Configuration columns, you're going to see different letters. You're going to see like GT. GT is a go-to. So it gives it 1 second. And if this is off, it automatically jumps to or goes to step 8. So the T part of it, there's a time associated and it goes somewhere. Go-to steps, you could have jump forward or you could have it looping. You could jump back. Some of it, you'll see steps that give AT. So PC roughing valve closed, check on. It gives it 15 seconds to see if that is closed. If not, then this abort fail defaults to this 999. If this condition isn't met after 15 seconds, it runs an abort recipe. And the message that comes up here, that's the timeout message. If you don't have anything here, it won't generate something. This is what you want the user to see. So on the PC vent, if the pump is not enabled, then it jumps down to step 8. If it is, then it closes the roughing valve. Make sure the roughing valve is closed. Then it waits 3 seconds. Then here, then if that condition isn't met in 15 seconds, then it runs the abort recipe. Yeah, remember yesterday when we had that red bar? Yeah. And this sets a carrier gas flows, which the carrier gas is what vents this. On that chamber, you'll have a vent valve that vents up the chamber. The same carrier gas that's used for the process is also used for venting on here. Then it waits for up to 200 seconds for that back switch to come on. If it goes over 200 seconds, like if you didn't have any more argon gas, it'll run the abort recipe. And then it'll say failed to reach atmosphere or ATM within set time. Then it goes and sets the flow set point to 50. It dwells for 10 seconds. And at the end of here, that's whenever you get that green bar. So PC vent will run that recipe. That's that pause step. That's on here. That is right here. Okay, so we're on step 2. Step 2, the recipe's paused with the same thing that's in the column. Do you want the vent? So we're on pause. We could resume from pause. If you hit skip, it does the same thing. It goes to the next one. And these are all the steps to that recipe. It shows what step you're on, what the value is. Or you can look at recipe tree. Eventually you become so familiar with it, you don't even look at it anymore. Now, on here, you can see it, the 600 skims, which is an event recipe. Is right here. That's at 600. And also the 250 and 250 here is these steps, 250, 250. So now we're at step 14, which we just hit. So now it's vented. So we can open that and retrieve that sample from yesterday.
Gotta do it now?
Just be careful you don't burn your fingers. So you know there's something on there.
Shall I put it?
Now, this is hot. You can put it down here, and this will actually act as a heat sink, not on a sticker. Just set it right there. Yep, a little bit farther over this way so we can still close it. This is there. This is also the heater. This is a heater. This is heater. This is aluminum shrouding. This is stainless. This is an actual heater. This is the heater. This O-ring, at the Kratos O-ring, if you close that, pump it down, and then you shut off all the heat, and then it's cool at ambient temperature, and you try to vent it, that O-ring's going to be sticky.
Yeah, yeah. I mean, so we have lower heater, upper heater,
PC lower,
PC lower,
PC upper,
exactly.
substrate heater.
Thank you. I
Yep.
understood. So PC lower, PC upper, and PC substrate. And
Just substrate.
heater.
Yep,
So, yes.
yep. And then
Because I saw
So this is a kind of deposition happened on the substrate. So I can see the color change.
yeah, because we had the wafer over here.
Right.
This isn't level, so it moved over a little bit. This color will change over time, depending on the thicker the oxide, the more color changes. So you have a little bit of deposition here, and a little bit of deposition there. But you definitely have deposition in there.
Obviously, like, we can see that.
Yeah, now this will eventually get to a point you won't be able to, it'll change.
Oh, really?
Yeah. Because maybe next time the wafer's over here, maybe next time. It'll change in different colors.
So deposition materials coming to the ground.
The TMA comes out of this hole into that hole,
Uh-huh.
and then there's a passage that brings it out of the air shower.
And the
So it drops down and then it disperses this way.
out from the air here, going here, and then
Yes.
What are these two holes?
These two holes is the purge gas from the argon that you see on the top of the vacuum screen, the one that changed to 600. That's you have argon gas coming out of here, and that leaks through these slots. That's what gives your laminar flow on the outside. So the precursor gas, you have some precursor plus carrier gas, so you have argon plus TMA coming through here, going up in, and then comes out of these holes and gets dispersed. You have other argon gas that comes around the it has a small barrier that helps keep the reactor clean. So this will change over time. So it's up to you. We can leave it as is, or we can put another sample on it.
That's fine, we can use this one.
Now, I don't, let me come over that there.
Well, the glass. Sapphire glass.
You can use two, right?
No, don't have to.
Oh, good.
Well, you have a coating, it's very hard. You can see, there's, if you had a new wafer, you'll be able to see.
Yeah, the color difference.
Yes, has a very slight hint of bluish tint to it. But more so, if you go back and forth like this, even on a 6-inch wafer, if you had a gradient of greater than 1%, you'd actually be able to see a color shift. There's no color shift. That's what I'm looking for right now. So the uniformity on this is less than 1%. That's just coming from my experience. But if you were to measure this on an ellipsometer,
Yeah.
you would see that it's very good. Now, by the nature of how
I think there
ALD,
is color change in this board. I mean, for example, the corners, color change. I mean, I want to address the extent of uniformity today for this. But because I can see color change in this circle, but not the entire circle.
I don't see it.
Huh?
Plus, this wasn't a clean wafer anyway. Now, sometimes on the bottom side, you can see that.
Oh,
So some of the ALD deposition worked its way under, but not all of it. It's up to you if you want to put that back on or
and
Yeah, we don't do any experiments, so we are training, so we can use it again.
if you want. Now, if you were to run 800 cycles, that would be almost a purplish.
now, so this is the result of 14 cycles,
400.
400 cycles.
Mm.
Oh, because the last cycle is.
Just
So,
able to know the balance.
What is your guess of the thickness?
There's legs on the bottom you can level it.
Okay, we can,
Yeah, there's on here.
yeah.
This is just rolled on here, but yeah, post underneath here. See? That's for that one. Yeah, but yeah, this floor is not level.
By that, we can level it.
Yep.
So, do you have any rough estimate of thickness for this deposition after 400 cycles?
Yep. They're really, really close to 336 angstrom.
300 angstrom is gonna be 30 nanometer, yes?
33 nanometers.
30 nanometer.
33.6 nanometers.
So, how long time, how much time it takes for 400 cycles?
Rounded by 24 seconds.
Yeah.
Divided by something.
9,600 seconds or 96.
Divided by 60.
A
To make it meter.
little over 2 hours.
Each cycle, how long it would take?
But
25 seconds. for each
about that.
Exactly 24.
20,
About that.
25.
So depending on what thickness, you just add more cycles.
I understand.
So after we had the sample one, now you could just hit, let's do this. So PC pump, this is the PC pump recipe. Okay. So it enables the pump, it turns it on, checks that it is on, makes sure the vacuum switch comes on, turns off the purge ISO valve, opens the roughing valve, and enables this phase. That's the statement that it puts in that black box. Then it waits 1 second, then it runs the gas recipe. So go ahead and hit PC pump. You can click recipe monitor. And already,
So it's
it
already
goes
green.
pretty fast.
Yeah.
Yeah.
It's fine, right?
Mhm.
That means it is good. Right?
That means it's pumped down.
Okay, that's right.
So go to vacuum. Right now, this did not reset that safety circuit. You'll see this quite often.
We have to
Enable
reset.
safety. Yep. Then this will come in. With that was that abort we did yesterday. I tried to run the process, and the safety wasn't reset, so it aborted it. So you just rerun the pump again.
Yeah.
Okay.
Can you let us know how did you calculate the thickness based on number of cycles?
It's fairly well documented. Aluminum oxide at 300 degrees.
There
You
is
get
a chart out there.
0.84. It's a known value. Now that's with aluminum oxide. There's a lot of
Depending on the
documentation.
material, I understand.
Yeah, some materials it may not. You may not know that. You know,
Yeah,
you
or
might have to.
not reliable, accurate. This, I mean,
Yeah, but if
correlation.
sometimes you just run some numbers,
I just
and then
opened
you-
it and it's paused.
you measure the wafer
Yeah.
on an ellipsometer. This way you got an idea of what the native oxide is.
Yeah.
And then you run a material on it for some number of cycles,
Mhm.
and then you do it on an ellipsometer, it'll give you a thickness. You take that thickness divided by how many cycles, and that'll give you your growth per cycle. And therefore, you can figure out what thickness you want. If you want thickness as far as material and you want it fast, that's the better tool. If you want really, really good quality film,
Yeah, uniformity.
uniformity and pinhole free. That's where this comes in.
Or now, I want to deposit a material like vanadium dioxide, so using a spiral. So I know that first I need to look for vanadium dioxide target from a company to circulate. For this one, if I want to deposit vanadium dioxide, so should I look for a TNA so that is related to vanadium dioxide? What I should look for?
I don't think you can do any dioxide depositions in the ALD. You'll have to do that via RF sputtering. So that example you couldn't do that on the system. Now you could do aluminum oxide in both, but you can't do what you just said. So
So we need to look
I
for
will-
other process.
So imagine that I want to do either aluminum or steel or any other materials. What should we change? I'm not talking about the recipe.
it depends on if a precursor is available to do that. Because you have physical,
Here
And
you
you
change target. That's it.
yes,
What about here?
the chemistry,
Chemistry, exactly which component?
whatever you're having for your precursor. That's what determines what you can deposit.
Exactly. This is what is called?
Ampule or precursor. So precursor reactant are used.
Yeah.
Both the
These
same.
are react materials.
Yeah, precursors are reactant because you got to react it with something else to
Exactly.
get something. That you don't have to react anything.
Exactly.
You already have the material.
Physical, not chemical.
Yeah, you're moving the material from one point to another point.
Exactly.
This, you're creating a new material
Okay.
because it's a chemical reactor that
that's
that
right.
creates it.
Okay. So I'm creating new materials
Yeah.
as a result of chemical process.
Yes, because you
That's
have the
why
aluminum
it's not
part
like it
here.
changes the target. I understand. So you need, so this one, if this is the case, this one can cover a range of, so materials to be deposited on the substrate. Maybe
It has its limitations.
So we
it
need
has
to,
limitation, I understand, definitely.
so we need to look for what kind of materials are deposited using ALD. There are
That,
specific categories or
Yes.
catalogs
Is that right?
which we can use as a precursor.
yeah, there are some very common ones.
Yeah.
TMA, hafnium, zirconium. Okay, those are all very common
Yeah,
for doing
very-
oxides.
So,
But it's open for any research.
It's there's different chemistry and different precursors coming out all the time. Yes. So depending on how well it's known or how well it's documented, like
Yeah.
aluminum oxide's been
Well documented.
being done for like 70 years.
Ooh.
So other stuff like cobalt, maybe not so much. Hafnium, doing hafnium, creating a hafnium oxide layer or zirconium oxide layer. There's, different benefits to different ones. They're very similar, but some people, because of the properties, prefer one over another, depending on what they're doing for their process.
Right. So when I put the PC vent,
This is the check step. Do you want the vent? Are you sure? So
okay,
you didn't hit it
so
by
I
accident.
don't need. So
If you want to continue, you hit resume.
if not, I don't need it. Close it.
Well, if you close it, then
Still.
that recipe will it'll stay stuck there.
So
So in this case, you can't hit stop because you don't want to vent. So you can say, I don't want to vent, just stop. Yep. So that clears up the recipe.
Yeah.
Otherwise, that it would be stuck on a step. So you can just close that or drop it off.
so now, with the use of the existing precursor, so what kind of materials we can create or expect to deposit?
For right now, it's just aluminum oxide because you only have TMA. But if you have hafnium oxide or TDMAZ, or you can do titanium oxide,
Using the same,
different chemistry. You'd have to
but
order.
it's still the same particular.
No,
Same, we need to change it.
yes, because you're changing the chemistry.
Like target, I mean, as we change target for sodium.
Yeah, but here you're using two different chemicals, two different components to achieve one result.
I understand.
This is, you're just taking the same material and moving it. So this is a chemical process. That's a physical process.
That's my question. So with the changing recipe as a result of this chemical process, using the same procedure, we can get different output materials.
If you're using
But this
TMA,
is a chemical process.
yeah, but you can only get aluminum oxide from TMA. You can't get anything else. So if you want something different, you have to put a different chemistry in there. So there's, like, if for some reason your process will require titanium oxide, you would have to either put PD mat on 3B or swap that ampule out. So you would have to add, you could still use the water
Yeah.
for your oxygen component, but you would have to change or add a precursor. The process itself will run very similar.
Now, my question is that you need to have a good understanding and deep insight about the chemical process in order to get your desired result for that deposited material. Am I wrong?
You have,
To develop a recipe which actually works.
you'll have to know what your components are to get what you want. The process itself will be very similar. The process of running hafnium oxide, zirconium oxide, titanium oxide is all the same as aluminum oxide. Visually looking at the process, you're not going to see that much different. What is going to be different is your end film. So you have to know what you want. It's not, you can't get zirconium oxide with TMA. You just can't get it. So you have to put something, it's called TDMAZ for zirconium oxide. And then you have the TDMAZ with the H2O, that'll give you a zirconium oxide film. So you have to know what you're mixing together.
That's my point. That's
Yeah.
my point. Also, the temperature, pressure. I mean, you need to have an insight on the chemical process.
You should have an idea, but that's also another thing with, well, you would use us as a resource. Because there's probably a good chance that we already have something or have, if we don't already have a recipe that we know will work, or we'll tell you it simply can't work on this and why can't it work, we might be able to give you a benchmark for where to start. And we always start on a conservative level and then work up from there. So I wouldn't shoulder that whole burden of understanding what has to be done with the chemical process and what you're choosing, because almost always it's somebody that sees something in a white paper or technical paper that somebody else has already done or experimenting and say, well, can we do this on this system? That's usually how that question starts. And then we say, well, yeah, if you want to do that, then you would need to order this and this and this. We'll go ahead and set up a recipe. If the heating needs to be adjusted or addressed, we'll address that. And then, okay, go ahead, run some samples, give us some information on what the characteristics of the film are doing. We'll tweak the process in, we'll fine tune it, and then, okay, this is a good point for this recipe to be able to run whatever you want. That'll give you your better chance of success.
I think in general, current setup will work for most of the metal oxide. Outside.
Yeah. In general speaking, yeah.
Yes, okay, yeah. What about ceramic? Ceramic. The other one?
Yep. Because you don't need RF sputtering for that.
So the current setup doesn't work for ceramic.
Probably not. Not that I'm aware of. That would be a Bruce question.
That's something requires upgrade, or it's
It-
better off using that?
Okay, for ceramic,
I,
maybe it should be plasma based, not heating based.
all the ceramics I've ever done, I've done with RF sputtering. Because in most cases, you're putting a barrier. Whenever you're doing ceramics, you're doing, some sort of barrier. Most of the time it's done with that. I don't know all the capabilities and limitations are of the ALD process. I refer those questions to Bruce and Noel. And it changes all the time. It changes as far as what's new and available. It doesn't change a whole lot on what is already in existence. So in the recipe editor, turn the list. So this is the only process recipe you have for the aluminum oxide. And I have some information I'll give you here in a little bit, but a lot of this stuff you can go on YouTube. And if you do a YouTube of aluminum oxide ALD, then there's a nice little PowerPoint demonstration that lasts about 3 minutes.
Yeah.
And then there's no gray area. It's like, I get it. And also with some other materials. There's a lot of documentation at different universities throughout the world have already had procedures that they put on. Depending on what their tool is, what works on the Oxford ALD system may not work here. Or it may need to be tweaked or changed. That's another scenario where you would say, well, we got this. I seen this paper from Duke where they're running this material on an Oxford ALD system. Could that material be run on the Lesker ALD system? It's going to be yes, but the parameters might be a little bit different because it's a different piece of equipment. This is better than an Oxford system, but it's also a little bit more money too. The recipe for the AB recipe, meaning TMA H2O up here, is similar as far as lines of the PC pump and PC vent recipe, but what is different is the sub recipes. So the first step here, it just changes your scan, it sets your scan interval at 1 second. That's just the computer speed for the lines. Then it automatically runs a sub recipe. The sub recipe, you can click on a recipe, it just does a check, make sure we're not running another recipe. Since I was in a sub recipe, I can come back to the master recipe. Then it sets an abort recipe. What do I want the system to do if things don't go as planned? That's this abort process recipe. Then it runs a sub recipe for your gas flow, which we've run a few times now. This sets your gas flow for your process chamber and your source gases. There's a dwell step. This is, step 5 is another sub recipe. This is what populates the matrix as far as what we've seen in the process. So that'll put all this up here.
The process parameter.
Yes. In
That
this,
experimental design.
yeah, as far as this matrix, this populates a cell. This is the sub recipe here. I got to come back into here. So here, this right here, define ALD. Yep. Then this sets a process phase.
There is no edit option, right? What do you do? Like, an ALD process parameter. What do you mean? What do you define?
You're telling, okay, TMA H2O. You're putting the process parameters in here. So if you're running different chemistry, that's not going to be the same. You know, the step will look the same, but instead of TMA H2O, maybe you're doing TDMAT and H2O.
So that will be done on the screen previously, right? Did that screen? You change the name if you have 2 precursors.
That would change it on this screen.
Yes. So
Yeah.
that's automatically change will come here also on the recipe there. Yeah. The name also will come, right?
Which
I'll tell you
name?
what I mean. So now.
But you're gonna load a different recipe. That recipe will have different.
Yeah. So we have.
This? that?
Yes, yes.
So this
No,
goes
we have-
by the recipe.
Yeah, MA plus
So you
H2O.
have a new recipe.
So if you have a new recipe, automatically the name will be changed here. Oh, sorry.
Well, you would create a new recipe. The new recipe would look almost identical to this, but this step right here would be different. This,
Yeah.
the wording of this step would be different. And then whenever you open a recipe, this will give different. So if you were running TD mat versus TMA, you'd have TD mat here. You would have a different sub recipe, and the process recipe would have a different name.
So, question on the recipe. So
That's
when you
my
talk
question.
about you have different recipes, do you mean you already have something to create, configure like this? You will send to us, we just load, or it's something we
Need
kind
to
of
fill.
configure,
Yeah.
create a new.
Well, what would be best is for us just to load the recipe, and then you see the difference. That would be
something like this, but you load into the system. We can just from the drop down button, we can choose which one to.
yeah, exactly. So where this is back here, if you wanted a new recipe, we would add that recipe in there, and then you'll have a different line. You might have a couple of different sub recipes with it.
Who can add that?
We can do it.
Here?
Anybody
Or-
could do
or
it.
remote.
We could do it remote. Let's-
Where you have to be you have to be told like we're
Oh,
going
the-
to add this.
Have the what's
We could do it through TeamViewer. Yeah, and then as you see different recipes and the changes of different recipes, you would be able to do things yourself if you chose to. That system, I would recommend, yeah, if you want to change something, change it. Actually, what I would do is I would take an existing recipe, copy it, and then change that. This way, if something gets boogered up, you can still go back to something that worked. This system, I wouldn't do that until you get a lot more experience.
That's why I asked you how many inputs you need to, developing a recipe here, needs
Yes.
really experience.
Good experience.
We would just put you another recipe.
Yeah,
And then eventually you'll see, oh, okay, whenever I have another recipe,
yeah.
90% of it's the same, but maybe only, 10% of
yeah,
it changes.
Yeah.
So, okay, all the recipes follow a similar format, but this is just changing. Then it becomes clear. But there really isn't a whole lot to compare that to.
Are you aware of like ITO? Current configuration. Same thing does also.
I don't know if ITO is done on ALD. It may.
But AZO.
I don't know. I'm not sure. I think some of those present problems. Indium, I wouldn't do indium on here. Even if it could be done, I wouldn't do indium on here. I'd do indium in there. That stuff like
Yeah, but I saw people do it. Not be necessary. So I just wanted to-
maybe indium. I would definitely stay away from indium in the system. Zinc, the stuff like depositing bubble gum. It sticks to everything. It's real soft and it's horrible to clean up. For that reason, I wouldn't do it in an ALD system. You could do it in that system and then foil everything up because it creeps. It's really weird. It's not indium, especially if you're doing like indium bumps and stuff like that. It's best to protect everything as much as possible with foil and tape because it'll creep into little small places for like if you have a crystal shutter that has an actuator, it'll eventually work its way into the actuator, the mechanical mechanism, and then it'll start dragging. Indium's weird stuff. But stepping back to this process recipe. So it loads up the matrix here, which is to define parameters. Then it sets a process phase. This is where it zeroes the counter. Current thread, this just changes the speed. The interval, when ECC interval, it changes the speed. Sets process active. And then it sets this recipe, which is the timed part of it, the precision time part of the ALD, what makes it go so fast. And then it runs a recipe and it just loops back. It goes through AB, then it checks the counter. If not, it goes back and loops, and it goes back and loops. Then once it's greater than or equal to, so it incrementally increase the count. Once they're equal, then it says, okay, finish up. So it turns off the process active, stops ALD, changes your scan interval so you don't need high speed anymore. And then you have a 2-minute dwell to complete any kind of reaction. Then it sets a process phase and it clears the reactants out of the matrix. And
These are the steps.
those are the steps of the process. So you can think about that. We can do lunch now if you choose. Then after lunch, we can run pump, vent, do the operation,
Yes.
shut down.
Normal phase.
What you're going to do, normal, get all hands on.
Yeah.
Do the exercise for that for a few hours. Once you're comfortable with that, if we want to, we could go ahead and shut it all the way down or bring it back up, or we could do that also. Then we'll go ahead and fill the water ampule.
Yeah.
We'll change the water ampule.
Right.
We'll do the conditioning phase. We'll do the pump purge. Then we'll load it. We'll do the pump purge again. Then we'll do the conditioning on the water ampule, and you'll be back to where you're at. At the end of the day, we'll go ahead and shut the precursors off manually, the manual valves, and then you can make a determination of how you want to leave the system overnight. After lunch, whenever you're doing a lot of the hands-on stuff, I'm going to start getting a file together for you for the procedures that we talked about. And then I'll put the procedures on the desktop or give them to you on a flash drive. I'll put them on a desktop. Plus, I'll probably have some other information. I'll just create a file.
All right.
Does that sound okay?
No problem. What time shall we meet? Now it's 12:30.
1:30, 1:15?
1:30 is fine.
Does that give everybody enough time?
Sorry, what?
1:30.
1:30? Yeah. Okay.
Right. All right. We will be around, so you better go and come.
Okay. And you could go ahead and pump and vent and whatever you want to do now.
No, it's okay. When you come back, we'll do the basic things.
Okay. Because then
Yeah.
this is the part where I step away.
Yeah.
When everybody gets their fingers. Who?
Yeah, we'll take that.
Okay. So we'll just be back at 1:30.
Yeah. Yes, sir.
One second.
Yes,
Um,
like 15 minutes.
about 5 minutes. put a recipe on here for conditioning. We'll check it out whenever we go ahead and swap ampules.
Just here, you want to.
Yeah, you can run it however you want to run it right now. Pump, vent, run a process. Anything you want to do, or whoever else comes.
Yeah.
Click on the different screens,
And
go
see.
to recipes, get acclimated with it.
So whenever something comes here, operation, vacuum, we have to, everything has to be on, like this one, right? So,
Have to be pumping, have to
Yeah.
have gas flow.
yes.
Your manual valves have to be open and have to be heated.
All right, so, we have to start from run recipe and ALD heater recipe. This one, right?
That's what you have now.
That's what we have to switch on for the recipe,
It's for heating. Yep.
run recipe, is that okay?
Yep. I'm gonna start building a small folder.
Okay. So this recipe history is based on whatever recipe available in the recipe editor. This thing,
That's from that recipe.
editor, right?
That's
From-
all the steps in the recipe editor.
These are from here, whatever you have showed us earlier.
Yep.
Let me, so this one was what I learned is ALD heater recipe, okay? Recipe editor. ALD, this one, right?
That is the heater.
Right,
Yep.
this
Click
one.
on that.
So this will run as soon as they say run the,
That'll put the set points and turn the heaters on.
yeah, I mean, based on this one.
Yeah, that's the one you have right now.
Like 41 recipes will run.
There's 41 segments in that recipe, not 41 recipes.
Okay.
There's
In one
41
recipe,
steps.
41 segments.
Yeah.
So 41 segments will run.
Yeah, there's 41 steps. A step can be a recipe.
Yeah.
So a sub-recipe, if a sub-recipe has 10 steps, you'll only have one line on the master recipe, but you have 10 steps in that sub-recipe.
It is all parts of one recipe.
One recipe. That's for,
Now in the configuration, you can R on there,
yes.
you can click on that. So in this heating recipe, that's what gives it a ramp rate. Before on the heater screen, you can put a ramp rate and a set value. This does it in a recipe. That's how it looks like whenever you have a ramp in a
Around
recipe.
10.
That'll be 10 units
Yeah.
or
This
10
was,
degrees over a minute. So that R is a ramp. So you have G, a T, G's go, T's the time value, A is there's an abort step, R will mean there's a ramp, or if you skipped it, you also see an S. So those are all the letters you'll see in that column, or none at all.
A is for abort. T is for time. S is for
Skip,
skip. And another one, G, T,
R, R
R
is for ramp,
around.
and G is go to.
Yeah, good. So these are the configuration available in the recipe editor.
In that column. So the ALD process will use an R for a ramp for heating. In the PVD system, you could have an R for power. Or if you wanted to ramp up on power, R in the software would do the same thing.
So S, there is no skip here, so,
You don't have a skip. Those are skipped. So there's
Yeah,
an S there because it's skipped in the column preceding. See the check mark?
yeah.
So that's skipped,
Oh, this one is not,
not skipped. So there's no S.
oh. Oh, okay.
You'll get used to seeing it, and the manual covers that a little bit. Whenever you go through the manual, you'll more pieces will start to click.
So whenever I want to go back to here, I have to click this one.
Well,
If
that-
I exit from here, from this
The
window.
recipe editor gives you all the recipes.
Yes, if I want to exit from here and go here or somewhere, recipe, I can click this one.
Yeah,
Directly.
look at it. Or if you want to just look at a screen,
Where is that?
click on one of the screens up the vacuum deposition process.
Right.
Yep.
Oh, okay.
Yeah.
All right.
So,
That's what-
generally, what metal oxide is better to be deposited using the sputtering, and which one is better to be deposited with ALD?
It depends on what you want to do, what characteristics of the film you want to have. So if you're doing, if you want to have a barrier layer on a sample that you're going to stick in an etching source, I would use that because you can put a thick layer fast to the barrier layer for your next process. I wouldn't use the ALD tool as a barrier layer because it's slow and the chemistry is more expensive. So, in that's what I would use.
Is another aspect. All right. Okay. But so I see that target for some of the material are also very expensive. For example, the target is bought from Lesker for vanadium dioxide or something around 2,000.
Yeah, but you're getting a lot more material.
But yeah, many because
You're talking ounces to grams.
You're right. Definitely.
Now with that, oh, that's a good point. With that, especially if you're using precious metals in here, we'll recycle that. Kurt Lesker will recycle that. So if you have a gold target or a platinum target in a sputter system, you don't etch the whole thing. You etch eventually, it's called a racetrack. You etch part of it. So if you get to 75% of your life of your target and you're running gold or platinum, you can send the target back to Kurt Lesker and we'll give you, value on the reclaim of that precious metal.
Yeah.
So you could do that and then get another gold or platinum target or whatever.
So once I did this, the next step will be PC pump. The steps in run recipe.
It'll start it.
What's that?
If you click on one of those, it'll start it or you'll get a pop-up. Like in a process recipe, any
Now,
step,
now I switch on the machine. I'm inside the machine. So the procedure, I should start from run recipe, then keep doing this one, right? Now I'm switching, after switching on, and maybe after 2 hours, after the heat is already done or whatever.
yeah, I would check the gas bottles are
Right,
open,
right, right,
compressor's on,
right.
manual valves are open, and the run process.
ALD, this system can be just aluminum, not aluminum. Just with metal inside.
You have to have a reaction.
Exactly.
With the TMA, if you just ran the TMA, once your aluminum is grabbed on to all your sites, that's it. You don't build any.
Yeah, so as a conclusion, I need to conclude some stuff for myself. As a conclusion, is not a good system or is not possible to deposit metals. Just metals, not metallic salts.
I wouldn't use, you can't use it to supply the country. Deposit, this grows. Grow films here. Build films there. So in order,
What is the difference? That's very important terminology. This is growth system. You are right. So what does that mean?
this per cycle, you build one monolayer.
Uh-huh.
You can't have another monolayer unless you have another cycle.
Yes.
That just builds and builds and builds and builds. That piles on. This, the two precursors react, one monolayer. Two precursors react, second monolayer. Two precursors react, third monolayer. That is rate. Rate
Yeah.
and time. Like shovel.
Right.
Like,
Right.
yeah, that's like shoveling material. This is building.
Yeah, that's why.
So you have a,
It's like additive manufacturing.
yeah, I
Add
can't even,
layer by layer.
that's atomic layer deposition. So we're on Wi-Fi, right? Yeah.
Let's do this. Here we go. Real simple.
Are you trying to show me that?
Yeah.
Actually, I think I'm using the same thing. This will explain what happens.
ALD process? Would it have capability at like ozone?
Yeah, you could add ozone to this.
Okay, because I saw one article on the ITO, they use ozone.
See, this is a really complex structure. But yeah, you can add ozone to this system.
Okay. You know how much roughly it costs?
We don't know. And that's your next precursor reacts. Parts of the molecules break off. They go to the pump. Now you have one solid pinhole-free monolayer. Your second precursor comes, reacts. Some of the molecule breaks off. And this is your cycle. Then you have a purge time. Then this is the dose time. It reacts. Once you reacted with all the sites, there's no more reaction. That's within the term self-limiting. So you could build layers like that. Again, no holes. That you're going to have holes in your layer.
It's some sort of additive manufacturing, I'm saying.
Yeah, it's better manufacturing.
Yeah, it's
It is.
additive
Yeah.
manufacturing.
Atomic level.
See, in this, you can have, again, conformal and pinhole free. So you can get in all the little nooks and crannies and super small areas. You can have very high aspect ratios and have a conformal coating all the way through any type of three-dimensional unit. Very difficult to do there. Good to do here. So this is half new oxide, but it's a very similar process.
So basically, if you look at the one sample we cut, right? So you're gonna place them this way, chamber. But it
Yeah.
will grow inside as well.
Yep, it will.
It will grow.
As long as we can close it, it'll grow. Maybe not so much on the bottom where it's touching the substrate heater. The rest of it will grow, yeah.
How do you deal with that? You just have something spacer?
You can, yeah.
Is that typical way you do that? If you want to coat it all,
That's how I would do it, yes. And then this way, instead of using the substrate heater to heat your sample, you're using the reactor as an oven. So you don't have any very direct latent heat transfer by convection because you're not touching so much. But you have a whole lot of latent heat transfer via radiation because of the oven. So yeah, you would have to have longer time for thermal equilibration. But yeah, you can do that. Or you have a
but
little.
your thermocouple only monitoring the heater substrate.
True.
So
Save not enough time.
if we put this sample, the chamber inside the wall will be coated?
Yes. In here, not in there.
I know.
So that's
Because
what
it is gas, it will go. This one is direct. For
I mean, the entire volume of that chamber, will be exposed, the materials.
Yeah. So you can have essentially a nanoporous structure, three-dimensional, and still coat everything in and out, very conformant.
So yeah, that's the biggest advantage of this one there.
One of the very big advantages.
Yeah.
That's one thing this can do that that
Yeah,
can't.
I mean, regardless of uniformity, I consider this one the biggest advantage.
Yeah, uniformity, the ability to have a uniform conformal coating, three-dimensional substrate, you can do here. Not there. You're not going to have
That's
conformal coating.
correct. It's three-dimensional.
Yeah. So if you have this, essentially, if you wanted to coat inside here and you put this here and you had the sputter
Yeah.
gun, you're going to coat a lot around here.
Yeah,
But up in there, you're not going to get a
Yeah,
whole lot
no.
for
You can see them.
a whole lot of reasons.
Yeah.
Here, you'll have a chance of doing that. Now, most of the structures that go in there, you can't see. You can't see all the little nooks and crannies. You know, if you're in a microscope, you can't see it. So it'll coat that. This is like throwing the particles of material that you're sputtering are not going to be all the same size. Okay. Visibly, it'll look the same, but structurally, it is different. So you'll have a lot of holes in your coating. You won't have any holes here.
Yeah.
So depending on if you want a barrier to protect an area that you're not going to etch, maybe this will be good because you can have a very thin layer, and since there's no pinholes, you can achieve that protection on a thinner layer than a very thick material. If you're taking a substrate and you want to have a barrier, and you're going to etch that barrier to create another layer on top of it, you would have a thicker barrier, especially if you're using like RIE, because the ions are going to just pound anything that's on top. It doesn't matter what it is. So it depends on what you want to do. This is usually a step of a multi-step process to build something. You know, this is just one layer or one step in a process. Some people, if you just wanted to have 200 nanometers of aluminum oxide and the quality really didn't matter that much, cheaper and faster to do it better.
Yeah, that's the sentence you mentioned yesterday. Now I'm getting better. So that's why you said that this is very directional. But that one is what?
It's very.
It's chemical.
Yeah,
It's
So
grading
it's a
chemical.
chemical reaction.
As long as the molecule can get to a spot, you'll be able to build a film.
Yeah. So the materials coming out from those holes. I mean, from
Yeah, it-
top,
It
so
comes
will
up and then
occupy,
drops down.
will occupy uniformly the entire volume of that small chamber, am I right?
Most of it. It's designed to go over a 6 inches, 150 millimeter wafer, but it's also designed with laminar gas flow to keep the molecules from sticking to the wall. So the farther out you get from center, the worse the uniformity you'll get. From 0 center to 150 millimeters, it'll be less than 1%.
By 150 millimeters.
Yeah, 6 inch wafer. You'll have less than 1% uniformity. That's design, that's by design of the equipment. But outside of that heater, now you're gonna have laminar flow coming in all over the place. So you're not gonna be as uniform from the heater to the wall of the reactor. Because you have other forces playing a role.
But your laminar flow, is that just going straight up? I guess so.
You have the heater, and then you have the reactor.
Yeah.
And you have carrier gas flow coming from your precursor.
Yeah.
So the carrier gas and your precursor will come in on the top
On the
and
top,
come around. But the heater sits up, and remember them little grooves? The gas comes in and goes around the heater too.
What kind of gas?
Argon.
During the process?
Oh, yeah. That is this gas.
So
That-
that's always purging in kind of from surrounding the heater, they're always coming.
Yeah, schematically, this is incorrect because it looks like it's coming in the top. It really doesn't come in the top. It comes in the bottom. Remember, we have the two holes on this side. This is the precursor. We had the two holes
Yeah.
here, front and back. The two holes here, front and back, is actually,
Argon.
at that gas. You have argon as a carrier gas, and you also have argon as a purge gas. It's all the same.
And the two holes on the left and right, this one corresponding to the source 3.
Correct.
This is source 1. So depending on which cycle you're using, so they may be pumping gas from here, goes to that the top hose, going pumping down, and then once it finish, did you have argon in between to purge it, or it doesn't matter?
You always have argon coming through. Whenever you do a dose, you have argon plus,
Carrying.
plus the reactant. Okay, that's what'll give you that peak. Because you'll have some argon coming through here, 50 skims. So it's just argon gas. Whenever you have a dose, this valve opens. So now from here, you have precursor plus argon.
Like aerosol.
Yeah, that's not a bad analogy. It's more vapor than droplets. But, you know, if you want to think of it that way, that's a better way to understand it, yeah.
Yeah, okay.
So you can pump, vent, look at the recipes, run the recipe, whatever you want to do from here. I'm gonna start getting the procedures to set up on the desktop. We can talk about that a little bit more before the end of the day. But now is a really good time to get your hands on there, go through the different screens, look at the recipes, look at the interlocks, run recipes, and just get more involved into this.
Have you tried
What?
the process, entire process?
No, I just did, recipe. Oh, just did this one.
Now I got
Peter?
concentration. So the
this
deposition
one.
is as a result of
does this one do? Just keep temperature?
reaction,
Yes.
chemical reaction of gases inside the chamber.
Yes,
Yeah,
that's
now,
the reaction.
yeah, now I come to the.
It's a limited
Without,
reaction.
like,
Yeah,
or you
I
want
see.
something
DVD
steps.
you don't have those purge, those
They
purge.
will go with
You have
zero.
dose. That's CBD.
That's
So that's chemical vapor deposition. You're building, but you're constantly filling it in.
I got it.
So you can have a constant build
What does this one?
that is not one
R
monomer.
means,
It's a
R
constant build.
means reshape, no,
That
from.
is a chemical reaction. It's a continuous build,
What's the rest?
but it's different than the physical.
Yeah,
Rub is 10. It's in the recipe.
And I have
It's a heater run.
Yeah.
and
Heater
YouTube
run.
and
So if
just,
you
you know, the videos are so easy,
This one.
and it makes it click a little bit better.
That's
So there's
the heater run.
advantages,
right?
and with,
Yes.
with PVD,
Let's
you know,
pull from
there's
there.
E-beam, there's thermal, there's sputter,
Or the recipe.
there's different ways to get material from one spot to another. And they,
This is one.
It's very.
if you want to get in there, you have to sell it, but it's slow.
That's why you should learn very well.
But it's slow, I know.
I mean, you.
Yeah, so it's like,
It out
How do
nicely.
you run that?
they're
recipe?
they're not
With,
the same.
Thing and, what do you
There's
think it come out?
big
from?
advantages
From
here.
maintenance?
Temperature.
If you want to do
Yeah,
something
this one,
fast,
yeah.
that can be an advantage.
That one is a few minutes, that one is a few hours, up to a few days.
Just talk
Can be
through it.
depending on what you want. If you want to run microns,
Yeah.
your day.
One, no,
So
the
you're
source
also
one
doing a lot more
and
material.
this source
Yeah.
three. This, source one is for.
So
the-
one is,
And source three is for
This
the.
here we have. How
Heat,
you want,
PM, the
I
aluminum
understand,
oxide.
depending on the thickness you are
That's
looking for
heat
and the
source.
number of cycles. How many 400 cycles we can run it?
I'm not sure. I'd have to ask. I have no idea.
Oh,
So
I
this
have
is
to
the
ask
chamber.
that question.
Why don't you run the operation recipe and changes only do like 10 cycles?
Oh, we do that?
Yeah, coding, yeah.
Are you
Do this one.
charge and
Only do 10 cycles.
we go back to target.
Oh, sorry.
Yeah.
This is in,
That one
You
you
should
should
have to change total number of
Like the
cycles.
create-
Not
I
your-
think I'm on the recipe.
Here.
Okay, let me go out first.
No, you can add it to the recipe. You cannot just run it.
Add it to the recipe?
Inert gas
Because you don't know how many cycles.
takes
right?
away a role.
Sure.
But in that system, yeah.
Well, that
We
has,
have to,
Higher, it's higher.
let's run the recipe then.
yeah, this, it has.
But how are you gonna verify? Okay, you can click that, see what happens.
And vent, yeah.
Yeah.
Yeah, it's
So
everything,
that-
right?
More than likely.
Oh, this one you said.
You have
Yeah.
nitrogen in the vent gas.
And this one zero?
Everything else same, right?
Yeah, everything is the
Here
same,
is
yeah.
the road
When you load,
area
Yep.
and vent, yeah.
Yeah.
And you run.
Yeah, it gets easier the more,
Yeah, the concept is very
But it-
important. Yeah, without getting the concept, I mean,
yeah, you have to start from
yeah,
somewhere.
definitely.
we go back
Yeah,
to the process.
Over a period of time,
95,
it's easier to understand.
Oh, then purge.
I haven't showed that,
Reaction.
deposition diagram. Oh, you have, already started.
Is it depositing now? Running, right? Yes, already one
Yeah.
cycle is going. Yeah.
But why this one doesn't show? Supposed to show something to
No, nothing is here.
Yeah, it's clear. Should be show some,
Reaction phase is.
yeah. There should be
Let
some,
it vacuum.
kicking. Hold on. Are we supposed to see something here? We're running the deposition recipe.
Yeah, so you can see it here. This, sometimes this happened, I don't know why. Close,
So you're turning down.
and then, no, the recipe's still running. Go ahead, put admin.
Or,
Whenever we run a recipe, we push it down to the controller and it runs out.
So
So
if you restart it, how many cycles do you do?
it already has tracked. It doesn't restart. It's running now.
So the software will be able to read from the controller.
Yep.
Okay.
You'll see here in a second. Okay, so if you launch the software, click on deposition. It'll now click on process. Okay, now you're okay. So
6 cycles.
the graph starts again, but the cycle will continue.
Anyway, I'm running into this. So
Hmm?
just
Yeah.
gotta restart it.
Yeah, I think if you don't give a little bit of time between switching screens to allow it to graph the dock, then it gets confused. Whenever I go and I hit deposition, I allow to graph the dock, go in a process and allow to graph the dock, give like 2-3 seconds before changing, then I don't have that problem.
So always, one of the reactant is H2O.
water?
Most of the time with this, unless you get an ozone source. And then an ozone source, about have oxygen going into it, and about 15%, 13 to 15% will be converted to ozone. And then that O will break off easy from O3.
Ozone is basically adding another thing after the water breaks down the oxygen.
If you're using ozone, that'll be your source of oxygen. You won't use water. Because if you're building an oxide, you have to have a source of oxygen. The O breaks off fairly easy from the hydrogen. So that's the reason why water is used. O2, the bond, double bond, very tight, hard to break. O3, easy to break. So that's the advantage of doing O3. And then you don't have the hydrogen, you don't have the wetness at all. Both, I mean, all of it's a source of oxygen. On the LX systems, you have the option of putting the O2 into a plasma and then breaking off in the plasma to react an oxygen. So in regards to getting an oxygen source in an ALD system, you H2O, O3, O2 plasma. That's the three most common. Here in the LE, you don't have the plasma option. So now you're done with down to the H2O or plasma.
I saw you tweaked this yesterday time.
Yeah.
You said it was because you want control to be around summer value,
Yeah, I wanted to have about 30 millitorp.
30 minutes old.
Yeah. On a peak height.
Peak time.
Mm-hmm.
So this is not.
To just finish the recipe.
What do you do that 30 minutes for?
I'm saying. The 30 millitorp is the height. So here, So this is just ALD cycles, but this is your pressure. So 615 because it's auto scale. This scale was a lot larger whenever you get the heights. So I wanted the peak height to be around 645, 650 millitorr.
Right now, you don't see it.
You don't see it. Well, you can go ahead and run the recipe again. Go ahead and run the recipe again.
Yeah, this is torr. Am I right?
Correct.
So, and,
This one, how
Yeah, same thing.
This one,
Yeah.
0.
Or 10.
what does
10.
that,
Ten.
what does,
This must be 10
Chapman
and the other
pressure,
one
what
0.
does Chapman?
You can
Okay.
do that then. The 600, you can make that 0.
Zero.
Good. What was your question?
Chapman, what is Chapman?
Chapman's capacitance manometer. So you have a range of 0 torr to 10 torr. Anything above it won't see.
Want to check the pressure.
So that's a TMA. Has a peak 650. Okay with that.
So the 650 minus this, right? So
Yeah, so it's the delta. Yeah, so this is higher. That's 665. So I'll go here. I'll change this now. I can do this. I can't remember what I made yesterday. I might not catch it on that cycle. Might have to wait to the next water. Because TMA water, TMA water. TMA, okay, this is for 10 milliseconds. Then your purge 10 seconds. Water, 8.5. We should see it now on this one. Not that much difference.
So this A is because this is automatically loaded from the recipe, right?
Mhm.
So whatever we put in the recipe. A means the first. B is the second.
As far as they're reacting, yeah. A little bit smaller.
So the 30-minute toy is recommended for this particular material or across the board.
No, this particular material.
So this one, that means only have 2 steps. Step 1 and 2.
Yep,
Then we have 4.
yep. So drop this.
It's like an orthogonal array 2 by 2.
What?
It's like an orthogonal array 2 by 2.
Uh-huh.
If you have 3, it will be 3 by 3.
Now you can get into, if you're doing high aspect ratio stuff, and maybe you need a little bit more material, that doesn't mean we'll go to 90 millitorr. What we can do sometimes, we can do multiple times. So it'd be TMA, 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 then water. And instead of having a 10-second purge, we'll do TMA 2 seconds, TMA 2 seconds, TMA 10 seconds, come here. So there's lots of things you could do with that. So I'll change this to 7.8. Right now, I'm going to do a little bit more training here. I'm going to add this to 20. I can come in here. Now here, TMA goes H2O. I'm gonna change this. See, that's where to disable edit. I'm trying to click on this to change it. And it's saying, oh, there. So, okay. Now I'm gonna change this to 7.8, so I like it where it's running there better. And I disable it. So now I've made that change.
So it's saved automatically.
Yep. Recipes you don't have to save as. You can make that change and it saves it automatically. So what's it look like if you start to run out of material? Which will happen. So close the water valve. Yeah, the water valve. Yeah, close it.
Right?
Yeah, close it. Pop pipe. Now, as the ampule empties, this will be more of a curve, but you lose the peak. Just because you lose the peak, you can open that again. You know, that can be a symptom of a failed solenoid valve too. It'll have the same symptoms, so you have to look into it a little bit. But you'll lose your peak. It could happen at any point in the process. Once you lost that peak, even though you're dosing material here, that is not adding to your film because there's nothing to react to. You're wasting it at that point.
So your software itself doesn't stop automatically.
It stops by the cycle.
So it's not gonna detect whether
No,
Could you please repeat it once again? The point is.
if you lost one of your precursors,
Uh-huh.
then even though you might get peaks after it for the TMA, maybe the TMA keeps on pulsing 50 cycles, 100 cycles
Yeah.
after, there's no other points for it to grab onto.
Yeah.
So the film stops. You don't build anymore.
Mm-hmm.
After that, it's nothing.
Yeah, you just waste it. It goes right to the pump.
So the step is one upon another, is the reaction. So one reaction lost. So it will be a
There's
crumble.
nothing to grab onto.
Yeah.
Yeah, yeah. Exactly.
And if
So-
you wanted to change this, you can click on here and change this display.
This happened because we switch off the water.
Yeah, this part. We shut the water off, had a little bit more, then almost nothing, and then we turned it back on. Now, whenever you're running out, it'll be much more gradual. It won't be as rapid.
forward, right?
Huh? Somehow, something.
So we might have couple of reactants.
This is from 2017. What's the ALD application? The energy cast, solar panels. Okay. I'll include this as far, because this was given during a presentation, but I'll include this for your information that you can look over. But, and it's a bit dated, again, 5 years now. But it gives you a little bit more information on ALD.
A lot of that is
Yeah, so it goes into emerging materials. I don't necessarily have the workshops and stuff, because this was given to their presentation. So I'll give you that. There's an ALD workshop. Let me see here. What do we have here? Okay, so here's the different oxides, some metals.
Oh, that's from liquid.
Yeah, but this is an ALD general. This isn't necessarily.
how about a gold?
Don't know. I don't think so. So here's the TMA H2O, the process, the chemical process. And that's with O2. See, it's a TMA, aluminum oxide, TMA H2O. This is O2 plasma. You don't have O2 plasma. Okay, but this is what you would have for that. Nitride, you can't do this, that's for LX.
What do you mean? Even with the upgrade, you cannot do.
So this is built a little bit more for an LX system than an LE system. But some of the chemistries are the same.
There's something that only Alex can do. This cannot do.
Yeah, anything with EEALD or plasma enhanced atomic layer deposition, we won't be able to do one here. But I'll include, this is good information. I'll include it, but it might not apply 100% to this. But it's stuff that I keep on my computer all the time. If I have to do a class or a presentation, I just grab from this. It makes it very easy. But I'll include it to keep in mind, doesn't all apply to it, but it's a lot of good information anyway.
That's not something you can add on to.
You cannot add plasma to an LE. That would be an LX. Yeah, so on an LX, you can have a liptometer tied to the equipment, and you could watch every single monolayer via liptometry. So that would be your in situ. Now, the liptometer is looking at one point, so that's the one point. It's not measuring all of it. Now, if you do it via ex situ and a liptometer on a stand, then you can move the wafer around. And then you can have a uniformity idea. So I'll include just for more information to understand the ALD process loosely, but it doesn't all apply to this. Some of it will. The thermal AL203 is the exact same in the LX as here. The means of it getting there is a little bit different, but the chemical reaction and the thermal process is exactly the same.
So let me ask you this. So let's say I have a wick. I only want to deposit part of it. What would you use to use as a mask?
That is difficult in an ALD. In sputter, it's easy. You could do capstone tape or whatever. ALD it's very difficult. You'd almost have to have.
We don't know the chemical reaction happens.
Well, you'd have to have a barrier, such as like a photoresist or something like that. That now, if you're using photoresist as a barrier, then you're going to have to drop the temperature a lot.
Rate will be too low.
No, it just accounts for that. So your growth per cycle will be maybe a little bit less or a little bit greater, but the limiting factor is the temperature of the photoresist, the toleration of the thermal stress on the photoresist. That was your limiting factor. So you gotta set the process up to accommodate for that. And there's gonna be a little bit of give and take somewhere. You know, so maybe the process, okay, you lower the temperature because you have photoresist or something similar on there that requires less of a temperature. So your normal aluminum oxide, which is now 25 seconds a cycle, maybe instead of having a 10-second burst, you need to have a 20-second burst. Now you've doubled that step. It's going to take you twice as long to do a process at a lower temperature. The growth per cycle might not shift that much, but because we're at a lower temperature, we have to do a longer purge. So the process itself might expand out. And you could do a barrier layer on there with half of it. You can do, like, say, for example, you can do a capstone tape and do a barrier layer of can't say aluminum or aluminum oxide, barrier layer or something, and then put it over here, deposit what you want onto it, and then remove it by dissolving or something else that ain't going to impact the original coating from that. So you could do with, as long as you ain't going to have crazy etching or chemical erosion from underneath the coating, and you can have a barrier like that. What barriers they absolutely use, like, do they have math material that they use for ALD? I don't know that. That would be Bruce or Null. But this will just give you more information. If it applies to PEALD or anything like that, it's not going to apply in the system. But it'll give you more exposure of what's happening within an industry. This was an overview of 2018.
Post the seminars, workshops.
And Noel usually does that, Noel or Bruce. So this is an LX system, different from yours. Substrate size and everything is different. Wafer. We use the field sense balloon. It's nice, they're expensive. But this is the LX system, which is you don't have. But whenever you hear about EALD or an LX versus an LE, this is the LX, so you can see some differences here. This is a plasma tool, where you can go ahead and ignite the plasma.
Is there any advantage for the plasma-based ALD over EV?
Well, the LX, we do nitride really good because we have a patent on how we have it configured. One of the problems with nitride is oxygen contamination in the nitride via pure because of permeation on the O-ring. We have an option where we could do differential pumping, which greatly reduces that oxygen contamination by like a factor of 10. It's massive. But this is all LX stuff. I'll include it just for review. But this is an example of in situ ellipsometry versus ex situ. Here, have the gases. This gives a little bit of idea of the laminar flow. Yep, a different heater, but it basically works the same way. So up top, you have a shower head, a flat shower head, and it comes down the same way. And then you still have flow around the heater. So this is argon. This is argon and precursor mix. You know, argon precursor mix, and then whatever is not used comes around here. So we actually, in the ellipsometer ports, we put a little bit of carrier gas, and that keeps from buildup on here.
Kind of clogged then.
It just gives a purge. So this way, you don't have no molecular creep or adsorption working its way up to the lipsometer port. So it's just one of the ways we keep clean. So this is eventually, whenever that reactor starts to get like this, that's where you're going to want to do a clean. So this is all delaminate. Delamination usually corresponded to the film structure of the material that you use. It gets to the point of structure.
How do you clean it?
Foam tech pads. We sell cleaning kits. Basically, it's the same as wet sanding. You use water, different grits of diamond impregnated sponges, to just scrub it.
This is to heater and also the top part. The top.
The bottom inside the reactor, you take the whole heater out. You scrub the heater, you scrub the top part. Everything that you see like a discoloration, all that gets scrubbed. Now here's what your multi-source looks like. This is exactly what your multi-source looks like now. You have two valves and then you have full pieces in the other part. If you were going to use an oven with a flow through, this is what this would be. You could add a flow through if you wanted to in the future. Again, most of this is set up for the LX, but it'll give you an idea of some of the materials. Come to the next one. That one's not the LX is not as applicable for that. So
That is paper.
what do I have here?
And the-
Oh,
No.
okay. So this is just a small scale relative of how small you get into atoms. It's very basic 101 type stuff. I'll give you that. This is probably the same video.
I guess for us to get started, we should find the similar recipe has been used or developed. Any paper on that, and we come to you and ask for whether you have already something else.
That's where I would start the conversation.
Okay.
This is the PowerPoint of the aluminum oxide deposition and what's happening. This is just something I picked off the web some time ago. But this will help you understand.
Do you always get those precursors from Stern? Is that where most of the time
Drum Sigma Aldrich.
those two places?
Yeah. Drum, you'll actually have a label on it that says the tear and the gross weight. So you can weigh it to know how much material you have left. This one, I didn't see that label.
Oh yeah, we have the empty one. Maybe you can show us later how to start.
Yeah, we're gonna do that here in a little bit. Bear with me. Okay, that has to do with the UHC. Has to do with differential pumping. So we're not gonna go into that. I'll let you know what you need. More of the same. This is just a flow chart. This is just a flow chart. So I'll give you all this. This will help you get up on the learning curve much faster. Thought I had it here. Might be. Thought I had one more item to give.
Practice it.
Hmm?
Practice it.
Yeah, so the PC farm, PC plan.
No, that's all I'm gonna build up.
It's not having it from the make comparison between this system and the other.
I thought I did.
No other, but
I thought I did, but I don't know where it's at, so I didn't delete it. So you can go into, same thing, sputter YouTube. Metal sputter, aluminum sputter, silicon oxide, silicon dioxide,
yes,
sputter.
dioxide.
Silicon, ceramics and oxides, you're gonna have to use RF.
Yes.
Or pulse DC, if you don't have pulse DC.
Yeah.
So after putting the,
Ceramic is not an option for ALD at all, based on the power.
I don't believe so.
Yeah.
after putting a substrate inside, we need to purge it, right? We need to purge the oven.
No,
Or
the-
vacuum or,
No, you don't
we need to clean it, right?
Huh?
We need to clean it, like using argon or something. The system has to be clean, right?
After you put the sample in?
Right.
No, that's already built into the recipe. You don't
Oh,
have to do
the
any
system will do that.
Yeah.
We'll purge it and we'll clean it.
Whenever you pump down,
Right.
it starts to run an IDF recipe. So that gas flow cleans everything up.
All right.
So that 322 centigrade is temperature inside the
Yeah, 330.
It's the temperature on the heater
on
itself,
the heater.
on the substrate heater,
Yeah.
not the thermometer.
Exactly.
So what's the melting temperature of aluminum? Melting temperature of aluminum is,
Oh, it's over 600 degrees.
oh, so 300 is like,
Substrate temperature on the.
anyway, we need to read the theoretical background. We don't have any theoretical background. That's why we nudge you in a simple stuff also.
And helps.
So,
This-
yeah,
This will help more of an understanding.
yeah.
You can do I thought I had something on metal deposition. But I do not believe I have. I thought I had it in metal deposition.
So whenever we start the system, we don't do PC vent, PC pump, whatever. It's already no problem with that. We just do on the LED, the PR, the process of,
Yeah, because the sample's already loaded.
yeah.
So you would have done vent to open it up, put the sample in, CC pump.
Oh, we use PC vent to take out the part from the,
Or to load one in.
oh, we have to do that first. Otherwise it will not be open. Now if I want to open it, I can't open it.
Um,
I didn't know that.
so you can,
Yeah, I saw it.
pour all you want.
Yeah, I got it, yeah. So I have to say PC when?
Yeah.
PC when recipe pause. I should say stop.
Resume.
Resume.
And certainly I have similar documents for struggling because they didn't give us anything like this.
This is my own stuff.
Yeah, I know.
Um,
I really appreciate. So
I-
I think
I had a small, example of what the difference between sputter is, thermal, EV, and I don't know where that's at.
Yeah.
I think I made it. Have you Googled? DVD,
Yeah, I know. I know.
then you can YouTube, like, that's
Yeah.
pretty much what I had.
Yeah.
I think I may have needed it. Maybe. Here, look at this.
It will take like 2-3 minutes, huh?
For
Yeah? It will take like 2-3 minutes to,
event.
yeah.
Yeah. Now you'll be over.
Yeah, yeah, now it's. Really the specimen moves to the extreme direction. So there will,
You need to level it.
yeah, this
So
one,
like-
but there is no problem on the deposition, right? Deposition will be uniform, whatever.
Yeah, that'll be fine.
It moves.
Yeah, it moves. Wow.
Level it.
Yeah, it needs to
We
be
need
level.
to,
There's four posts behind the wheels. Maybe.
after loading, we don't do PC pump, right?
DC bump, yeah.
We do after loading.
Yeah.
Mm. Okay. PC pump is complete.
Why the substrate moves?
The leveling is
No,
not
no.
good.
Oh, leveling.
So once we do that, we have basically we need to do heater, but that's since it is running, no issue to do.
Yeah,
that.
I would hit the safety first, the safety reset. Immediately after that.
Which one is
immediately
safety
after-
reset?
On a process chamber screen. Underneath CDA.
Process chamber.
Safety circuit reset.
Oh,
I would make it a habit of hitting that.
that will let me know that, yes. If there is an issue, I have to go and resolve it.
No, if you try to run a process without hitting that, you'll get an abort. And then it'll tell you, okay, we gotta hit that. You're gonna see that again.
All right, now this is done. Next will be go to PR ALD.
Yep.
We don't need to do heater recipe because it's already ignited.
It's already hot.
It's already hot.
Just-
We did this one, how much? 10? 10 is for total number of LED cycle. So like go to under 100, whatever. Fine, yeah. Let's do for 10. This one is sample equilibrium time, equilibration time 0, 12. Hey, come to that.
This is part of the screen.
Yes,
For this screen.
it's a video. If you press completely, it will go.
No, my question is that this camera is with the.
Yes, yes.
Very nice mounting. Right. Sorry.
Yeah.
Very stable.
I don't know what is this, but why it's not showing me here, Thomas? It shows here. Yeah, but here it shows. Doesn't show me anything. That means so small.
Huh. Because it's auto scale. You have a big range here. You have 5 minutes, change that back to 1 minute.
Oh, I did 5 minutes. Oh, that will help. The green one is for what? Is it deposition?
Cycle. Number of cycle over time. My question is that this platform shows capability for multiple reactants. So, but the device also allow us to do that. The capability of configuring 5 reactants.
5.
Wow. Then one reactant always is TMA.
Unless you change it.
And you can change this one to another material.
Yeah.
Okay. So how about the other reactants? I mean, how to ask one question. One question is that
How to change the names, you mean?
no, for what kind of materials we need more than 2 reactants?
Most of it you'll have at least 2 reactants. But you might do aluminum oxide or titanium oxide layer.
Titanium oxide.
You do an Al2O3, then maybe zirconium. Aluminum oxide, zirconium oxide.
Who arranged that step? The system will make that arrangement?
You build a recipe for that.
Oh,
You have to have the
So
physical.
that recipe you will provide us.
This one.
We can provide that if you need that, yeah.
Otherwise, we don't do that.
No, you won't,
No.
you don't, you don't have the experience to be able to write a recipe yet. You just don't.
All is about development of recipe.
Yeah.
Yes. And it's just not about different chemicals and reactants. You need to have some insight on the proper operating conditions.
What is in there now?
Eh?
What is in there now?
The same material?
Yes, this is abnormal here.
Yeah, it's abnormal.
So see how it's fluctuating?
It's over. The cycle is over.
Yeah, but you see the fluctuation here?
Right.
That's this fluctuation. That's not normal. So let's look at something.
It's abnormal.
Not good?
Yeah, it's outside.
No. Could be better now.
Yeah, it
About
brings some
failure rate.
change.
Failure rate.
Yeah,
Failure
it's
rate
still something a little bit goofy. Zero all flows. This should not be happening.
Do you want this one?
You
No.
see how this is bouncing?
Right.
That's this bounce.
Should be fixed.
Something wrong?
No, I just seen a difference.
Hmm.
What does IGF stand for?
Inert gas flow.
When did you run this one?
We saw some
abnormal.
abnormality
Sure.
there.
Yeah, this doesn't look right here. This fluctuation is bouncing. See what the gauge says.
Does not happen as a result of opening the chamber.
Might. So I'm just doing a process of elimination.
Mm.
See, it's nice and steady here. That's what I would expect. So we might have a little speck of dust or something like that on the O-ring.
Is lamination of what?
We might have a speck of dust on the O-ring.
Mm.
So we'll wipe it off
Substrate?
on the O-ring.
Or
Oh, really?
or
Down.
yeah.
So we'll look at that here in a moment.
Okay.
We don't have any tech wipes. So. Tech wipes would be very nice. Some tech wipes. Not clean at all.
The O-ring.
Yeah. This is only particles. So we need to have some good tech wipes. And isopropyl alcohol.
You usually run this in the clean room, or it's not everything.
Some people do, some people don't. There's a lot more particulates in the air. This is not a good cleaning thing.
It's fluctuating.
Yeah. Yeah, I think there's dust on that O-ring. Yeah. Yeah, some good lint-free cloths and some IPA. Because I think this is bouncing around. And also the rate of rise. Will be higher than it was yesterday. Yeah, there's that O-ring needs to be cleaned.
Want to be keep what
Hmm?
what kind of value?
You should have around 10 millitor over a minute. Yeah.
What's up? We got their product.
Sorry.
Have this test that, yeah. What? Yeah. Thing is, when I don't have any cleaning device.
You need tech wipes. There's dust on that O-ring, creating a little bit of a leak. Need to have tech wipes or a wipe and a little bit of IPA.
Wipe, simply wipe.
Lint free. Has to be lint free. Because if you have a little piece of lint or a hair, it'll
Okay.
cause problems.
Atomic level, right?
No.
I mean, the problem is identified in atomic level.
It's a little bit higher. There's some dust on there. So we'll just have to deal with it for right now. The only thing you have here to wipe it off is a paper towel. And that's not going to cut it.
I don't think we can get some kind of wipe from Giant or something.
No.
Yeah.
A little bit better now. I might have got some of it off. This is better now. I think I got some of it. You're definitely going to have to do that. Definitely going to have to get some tech wipes. Because you're going to need it for that whenever you open out for the door seals. But this is also something we can do remotely. If something's running weird, you could just send us a team viewer details and ask, can you take a look at this? We could work through it. Okay. So this looks more normal than how it was. So that was just a little bit of dirt.
Wipes for cleaning electronics and lens, is that good?
It's, as long as it's wind free.
It's great.
Yeah.
Okay. So everything is okay now? It's good.
Yeah, I cleaned it off. I got some of whatever was there. And now we're back to somewhat steady. You don't have all that noise.
Yeah.
But
We have to clean it over time.
anything that, if you have a speck of dust that'll drop on there, that'll impact it. Same thing with this. They have to be very careful.
One thing I wanted to ask you was, you say we only have one source, right, for those two machines
For power.
for power. So I guess one question is how we shut it down and how we turn it back on when we need to use it. Because we might be switching.
We're covered that.
Covered that already? Okay,
Yeah.
good. And also the other thing is, we haven't been using that for a while. If you don't mind, to help show us, what, turn on, kind of
Yeah.
the procedure. But
Um,
he was not here when we
Yeah,
had
I
it.
was asking him this again.
I'm not as familiar, but I can figure my way through it.
Turn on. I think everything has been inside. We haven't really touched anything. We just turn it off. Well, no.
I totally understand.
So are you okay up to this point here? And if you wanted to, even though you only have one power supply for here, if you wanted to keep the computer powered on, just to get acclimated and go through the screens, you can still just get a regular adapter
Yeah, we have.
and keep the computer up. So I guess what we should do now is give me that other ampule.
Yeah.
Okay.
It's 15 milligram, sir. It's not 25 milligram.
What? How much?
15 milligram.
What? That's the ampule size. Is it the new cylinder? That's the same size. That's fine.
Yeah.
That's the same size. No problem.
Same, so yeah. What's TMA?
Okay, now that the process is finished, you're done running the process, you keep these closed.
So I'll close the TMA and H2O now. Yeah, you don't have to have it super tight, but no. Need a knife? Now on let me make this go away. Don't know how to make that go away. Here, I'm just gonna close this. I can't make this move. So here, this is the folder that I created.
Thank you, thank you.
So this is what I was showing you. Again, the LX does not apply, but here is this MP pump purge, MP vapor draw ampule, and the thermocouple placement is here. So these are your pump purge procedure and vapor draw. This is removal and installation. The ampule, I can't make that go away again. I move, I can move it, good. Okay, this is your pump purge sequence, what we did yesterday. And well, we have to do this again. So actually, if you can look, we'll need to do this first, so look for this procedure. Now, these are stainless gaskets. You could use them. I usually use nickel. ACS 3H2. And the orifice is much smaller on here. So for this reason, you usually take the valve off. Fill it. So you'll need to either have DI water or water, something like this. Do you have a graduated cylinder? We need to get, I need to measure 25 to 30 milliliter. Be a graduated cylinder, beaker, or something like that. So you run through this?
Yeah, it's great. Thank you so much. Thank you.
Well, then we can do this now.
Yeah, so I will study all of them.
So go ahead and minimize.
Never mind. Yeah,
And go up to here.
here.
No, yeah, like,
Where can you put your focus?
log in.
Like your place on this, yes.
Yes.
Okay.
Now we need to do that procedure on source one.
Give it to me. Phil, how?
Back. There. You 125, right? No, that's just fine. Yeah. The graduation's good enough. This is clean, right? Okay. So. You should be within, It'll be good enough for this. Yeah. Then we can save the stainless. And this is just water, I gotta think of water. Anybody else wanna do? Yeah, I'd rather study your hands. Yeah. Yep. It's a 50 ml ampule. And we're filling it about halfway. If you don't get every drop in there, it's okay. Try it. Doing much better than that. I'd have half of it on the place.
So you only refill water, or you can refill the chemical?
For this, I would just do water. So now, go ahead and put some bread in. You can just finish it up. If you notice, this valve has a longer leg on it than other. For some reason, they always put it so the longer leg's up. I don't know why. It's a ball valve, it isn't gonna matter. Okay, so here, on this gasket, you have 3 ends. You wanna put 2 of them on like that, and we'll snap it over. Without getting your glove in it.
So inside or outside?
Okay. You don't have to bend it. You can do it that way, or a lot of times I just put my thumb on there, push it up. So have that, and then do that on top of it. And pushing that up. No, not too, I found
The USB thing is not that big. We need one more range.
So here, this would be 3/4.
The big one, okay.
Yeah, so the crescent will go on the valve. Yeah. No, that's for this one. You'll have to use a crescent on that. I think it's probably like 7/8 of it.
So I should use this one.
Yeah.
There are 2 pressure jobs.
Or you can get a holder. Otherwise. Otherwise, you lose them. Yeah. I like water. Yeah, now, got it stopped?
Yep.
So now you can go, yeah, go about 1/8 of a turn more.
One more,
Yeah,
but they're not with.
yeah. Okay.
Enough.
That should be good. Again, wait till the 1/4 turn, they usually go about 1/8 of a turn. That takes care of that. We'll close the valve. We got atmosphere. Oh, fuck. So we'll just set that aside for now. So we can put that someplace. You didn't have the valve closed, the water would run out. So, let's say we ran out of the water. This is where you'll go do the pump purge. It's gonna be a while since months. That's where you go ahead and open a procedure. Which is pump purge. Here, let me make it bigger. Okay, here's a pump purge sequence. Oh, this is the removal. I don't know why that didn't pop up. I don't know where it's at. What's this here?
Close the fire. Close the fire.
Yeah.
We open.
The storage lock was out of water.
No, I think that arm is belongs to, that's yours, right?
I mean,
The one
the
side?
abnormal behavior of gap was because the storage lock was out of water.
No. No, we're just changing it because we're changing it. It had nothing to do with the water. You get a little bit of dirt on the O-ring. I don't know what happened to that.
Opening.
Let me go grab it again. For this. Yeah, it's there. I don't know what happened to it on the other one. It's just weird. I have absolutely no idea. I'll do it this way. There you go. It's not working from that folder. This. ALD materials. Okay, put it back there. There. Okay, now it's good from both places. So this is, remember we opened it 3 times? Okay. Make sure the manual valve is closed, which it is. Then open it for 10 to 30 seconds and then close it. Source X, where you're doing source 1. Okay. Then we need to do that 3 times. Yep. You don't have a flow through ampule. Okay, so this is what we did yesterday when we open, close, open, close, open, close. And then 0 all flows open it to get below 10 millitorr. That's where we were at yesterday. So you want to? You're all hands on to that. So, go ahead and minimize that. Since we're changing source 1 ampule, go ahead and minimize that. Open this. Go to deposition. So we're doing source 1. So we have the ALD IGF recipe already running what the procedure says. So open that. And then close it. Do that 2 more times. One more time.
There to see changes.
Huh?
There to see changes.
Well, this,
Not curious.
yeah, the gray will change. So this evaporated or exhaust or drew off the last bit of the water vapor that was between the ALD valve and the manual valve. So that is the purging. That's pumping it. That's part of it. You do. It's called a pump purge procedure because there's 2 parts. One is the opening like that. The other one is, the other part of that procedure is zero all flows, off all valves, and then open ALD out. Then it says, wait till it drops below 10 millitorn. Then once you do that, close the ALD out valve, go to run recipe. Yep. Repeat that 2 more times. No, zero all flows off all valves. And open that. Wait for it to drop below 10 millitorn. Then close that. And the ALD IGF recipe. One more time. Zero all flows. Off all valves. And now. Drops below 10. Close that. Now we're ready to remove that ampule. So that we can feel safe that any chemistry is gone. So we'll need the crescent wrench. I'm not doing it, you're doing it. One of you guys are doing it, not me. I know how to do it. All right. So you'll need this, this. And grab.
Yeah, I got you. I saw you yesterday.
Up here.
Yeah.
So we'll take this off. Yep.
The water inside the cylinder.
Put the auto on. We gotta get a new gasket. Is there a new gasket right on top of there? This one? Yeah, here. Use it. Yeah.
So-
Just I got gloves on. This is how I do this. I get it so there's 2 tabs.
And then.
And I push it over.
So this is veg wrap cylinder for reacting water and the other one for aluminum oxide.
TMA.
Yeah.
Together,
Together, I'm fine with the other.
not until.
if you have another reactant like alcohol, so you need to put alcohol inside this cylinder rather than water.
You have a difference in what?
If you have a different reactant for your material, for your deposition, which is alcohol, for example. So then you need to put alcohol in this cylinder as one of the reactants.
Most of it is gonna be doing oxide, so you almost always have water in it.
All this is
You
what.
might put something different
Yeah,
over
yeah,
here.
because of those
But-
reactants. Yeah.
The precursors they're gonna use for a reactant, usually because of an, they form an oxide, it's gonna react to the moisture and oxygen in the air that we're breathing. So you won't be able to just pour it in like we did with the water. That you would have to use a glove box or something like that. I don't know why. What are you doing? Let me see. Sometimes you have to hook it. It's a little warm. Yeah, really good. Okay. Hey, good. That's the way, yeah. You're not like me up a little bit. Okay. Sure. Yep. Thousand. Really good to start with, like looking it out. First up. See there. Good. Down on the leg. This time I think with a little water. Okay? Now, I'm not gonna do, I'm not gonna let you wash that easy. That's what's happening whenever you're spinning it, that much pushing up. Keep it down. I don't want to use that. See this? You see SS on it? It's stainless steel. It says NI, that's nickel. Nickel's a little bit softer. It's easier to get a steel that one. You can buy nickel, okay, David, for, that's what's happening, not it's pushing up. You gotta keep it from pushing up.
Stop again.
Yeah.
Come on. Got it? Yeah. You got it tight, you think? Maybe so. You want to tighten, you gotta be careful not to over tighten because
Yeah, that's what I did my best.
okay.
Yeah.
So, manual valve it off. Close.
This is closed, it's horizontal, yeah.
Okay, now you gotta do the pump first. Sequence again to get the atmosphere on between the manual valve and the ALD valve.
Why is this closed?
Yes. Then we'll do the conditioning.
All right, let me do first, let's do this one first.
Do the pump first. Then this way we'll test the conditioning recipe.
That's one, right? It's your part. Or it's effective.
Yeah, the safety, yeah.
Effective.
We switch off we turn on the valve, ALD out. Right?
Yeah, open and close.
All right.
And do that 2 more times. Now, if that was leaking, you would probably see the peak here. So if you thought you see the peak here, then make a longer time between the pulses. If you like pulse here, so wait maybe 2 minutes. And do it again. This looks good. This is the way it's supposed to look. If you see other little shark fins, then you have another issue. So
Do it one more?
you can do it as many times as you want. You have to do that 3 times. Then you have to zero all the flows off of the valves and then open that. And then wait till it drops below 10. And you can read through the procedure and it'll tell you to do everything that we're doing. Close that valve. Run recipe. ALD IGF. And do that 2 more times. Zero, all close.
All close,
All valve.
open valves, open this one.
Open. Wait for it to drop below 10 millitorr. Then close it. ALD IGF.
You want 3 times, service.
Yeah, this is all the pump purge sequence in the procedure. Plus, we just went through, there's also a procedure for loading and unloading. It just goes what we did. That'll be good reference because it'll be months before you do it again.
Fine.
Okay. So now we're gonna test the pump purge or the conditioning recipe I put on. So open up that water valve right now, the manual valve. Okay. Go to run recipe. Or go recipe editor first. Now it should be MRALD conditioning X. Open that. Second one, ampule conditioning. Open that sub recipe.
Done.
No. One more. Yep. Double click it, hit it again. Okay, that's fine. Return a previous recipe. Go to line 9 recipe.
Must be 9.
Yep. So this is where you change these names. Right now, we're doing source 1, ALD. They're doing the water.
Mm-hmm.
So if you were doing 3A,
Right.
you would put 3A. There's a pull down here. Yep.
So we have 3A, 3B.
Yeah. So that's the only one she'll be conditioning. So you change that depending on what amp you're conditioning. This is good. So return a previous recipe. This is not included in run list. So if you go into run recipe, you won't see it on this list. So we're going to change that. Come back, close that. Click on include in run list. Okay. Go back to run recipe. Now it's here.
Fine.
Yeah. So go ahead and run it. See how well. Yeah. Let's see if it'll work. That's fine. Yep.
Continue.
So there's only that step of the recipe you'll need to change. Go ahead, close that. Let's close that and go to deposition. So process, we're only doing reactant A, which is the water. So yesterday, this recipe wasn't on there. We ran a process recipe, we just kept the other reactant off. So now you don't have to do that. You can just run that conditioning recipe for any amp.
But you need to change source 1 and source 3. What you said.
Whichever one you're conditioning. Yeah. So now you got a designated recipe for that. In there, right here, this one says change. If I come up and I scroll this over, that ALD processor could change here. Okay, if we wanted to, we could go ahead and do something like let's do this to make it a little bit easier to identify.
Recipe.
Yeah, so now you can know, that's what's nice about the notes section. You can put whatever you want. So now you can say, oh, okay, this is the only one I need to change. So this is running 50 cycles. So when we did the pump purge, we evacuated the atmosphere that was between the ALD valve and the manual valve. Now we're evacuating the atmosphere that's between the water and the ALD valve. We're getting rid of it. This is going to be the conditioning curve that you're going to see. This is going to be normal on anything that you condition. Now, if you were to take that off, you close it, do a pump purge, take it off. If you reused it, you don't have to condition it again. You still have to do the pump purge because you'll have atmosphere between the manual valve and the ALD valve. But this just gets rid of all that. Then once this completes, it gets to 50, that water ampule is conditioned. You can go ahead and close it. And we'll secure this system and plug that system in if you don't have any more questions on this.
So by meaning conditioning, basically you are putting it into a near vacuum condition.
You're taking
Most of them.
the unwanted out. In this case, it's the atmosphere. In the case of an ampule, you'll get from Sigma Aldrich, you're getting rid of the packing gas. Whatever the packing gas was. It might be nitrogen, it might be argon.
So in this case, it will be like a water vapor. After you condition.
The what inside?
In the ampule, it will be the water vapor. This time?
Yeah, just, it'll be 100% water vapor. It won't be water vapor plus.
Yeah.
You know, atmosphere or whatever.
Basically means you're also gonna have some water coming out.
A vapor like you would do
Vapor,
a
yeah.
normal process.
It's one of the reactants.
Yeah, so you'll always see a curve. Usually within 25 cycles, it will steady out. We gotta talk about the ampule heater. So we'll spend 10 minutes doing that before we shut it down. So we got until this gets to 50 before we do our next step.
And that was a mistake.
We will keep practicing. Keep falling. That's where we will learn.
Yeah, that's good practice. Tomorrow, do it again.
Yeah, this.
You know, I tell my students, if you wait a day, you lose 80% of your memory.
Oh, okay.
With 3 days, you don't remember anything.
Okay.
Oh, okay. So then you can do the good news. So we got this other target, 2-inch. So we can install this one while he's showing us the
Wow, on time.
just on time. You have to.
It just required like practicing, otherwise not that much time.
We have the machine, yeah. But then the
Right.
next part is you have to find out the recipe.
Yeah, that is yeah, that's the second thing.
First part is
Never seen one of these.
It's definitely take a look at that.
Remember Lesker, I gave you another one 2 days ago? You said it's 4? You know where it is? This one you said 2, the other one you said it's 4. I give you the 4th one. It's like-
This one is taken out from the water clothing, right?
Hey, it's from one of them.
Same.
So one will be from the water, the new one that you had, one's from the TMA, and the 2 plugs are from what was in the system.
Keep it carefully.
I would keep that someplace. I would have like small toolbox or something like that where you keep spare parts.
You don't need this, right?
You don't need that.
For this one. For unusual control, have the target stuff.
Oh, what's this past yesterday?
So we run. Are you Spanish? For the money. Can't do anything. Yeah. But for this experimental part, so color is done.
It's not a real substance. Part of it.
Yeah.
Learn about it. Job often.
So the heater channels for 3A and 3B. So you see right now that 65535?
Yeah.
I'm on the maintenance heater
Yeah.
setup. Okay. So three, five, now. Next one down. 3A, control. I take the thermal couple here and I plug it in here. One of those change. Okay. So that should be 3A control, 3A temp one.
This just does.
Here's the other one.
Last one.
Right here.
There's two are the ones who have the 655 wedding, but only one of them.
This one and right here. So this is temp one. And this is the second temp. So watch, I'll unplug this one.
Oh, this one. Okay.
Yeah, okay, so I'm gonna unplug it.
Okay.
Okay. So this will be 3A. And it's not labeled, so you have to plug in a thermocouple and say, oh, okay, this is 3A.
Okay.
Okay. So
What is 3B?
next one down.
Oh, okay. So which one shall we use? The other one?
It depends on what you want to have heated. You're only going to, right now, PMA doesn't have to be heated.
Yeah.
So if you put hafnium or zirconium on 3B, then you'll put thermocouples attached to 3B.
So this is 3A.
One. Towards one.
Yeah.
PMA is on 3A,
Okay. What is the 3B?
right next to it on the other side.
Oh, so we have another one.
Yes.
Oh.
We have a chance to put five like this one. So this is plus three heater.
Okay.
Three.
So 3A, 3B, 3C, 3D.
And 3E, but you have positions for D, D, and E. You don't have the
We don't
valve.
have 12 hours.
Yeah.
But this one always water.
Yeah, this is a long feet water.
Okay. Or if you have ozone or oxygen.
If you have ozone, ozone goes back here. The ozone generator goes, this panel comes off, and the ozone generator comes off. And then there's some valves that are added right here. And then the ozone will come into here.
Okay.
The power supply for that gets added back there.
So straight A, B, C, D. Okay.
Yeah,
All right.
so if you are going to load,
So those first three either are for all the A, B, C, D, doesn't matter which one. Just a common line for all the source three.
yeah, it's on one manifold.
On-
So um, this, here we go. This vapor draw sensor placement. This explains that ampule now, where to place the thermocouple. So if you were going to run zirconium, you would take the zirconium ampule and you would take two sticky thermocouples here and a sticky thermocouple on the back of the valve. This one is just an extra. And these two are a precursor material there. Then you would put it up on the here. You could put the thermocouple, you could put it up there first, and then put the thermocouples on. Okay,
So those thermocouples plug into that three.
so that's it. Yes. They go in the middle couple.
Okay.
So if this is on here, then we have this, this would be in the position here. And you'd have them 30 plus. These thermocouples is tied away. Don't do that. So imagine this is here. Yeah, 3A ampule and 3B, they're laser. So since this is in 3B position, plug it into the two lower thermocouples, the TC1, TC2, they're short, which they probably will be short. Have these. Okay, that's extension. Bring that over.
Doesn't matter which type of thermocouple, K or T.
Okay. It does matter. Yeah. Now, you could buy these from us, or you can buy them from Omega. Have a couple of these sticky thermocouples. That's the valve. There's a valve blade. So, they're up in here, these are tied away. Tied away. You have the two thermocouples here. Okay, we're a little bit too short. We'll get the extension. I'll wrap this back up.
make the extensions nicely. Kind of like routing through the system.
So this first set under here would be A, we're going for B. So go ahead and plug it in here and here. You can come into your maintenance, make sure B's reading here and B's reading there. After that point, you could run amp-your heating recipe, which you have A and B. If you like, you can come into chart and go to heating too. And you come into chart, settings. I know where it's at, so it's a little bit easier for me. So you can do amp your heater temperature, temperature 2, and then I'll do temperature set point. So that's a real quick lesson on the charts. I'm bringing up 3 pens. Again, you can only have 10 at any given time. So I'll drop this. Now I can run a heater recipe. And you should see, if you wanted to come to here, I didn't reset the error, so it's not going to do anything. So I'm going to stop that. Close. So 3B still has an error.
Haven't enabled it.
Oh, I haven't enabled it either, but it still has an error. I got to clear the error. Yeah, because it doesn't turn it on. Well, it turns it on here. But I don't believe it clears it off. So let's do it anyway. Maintenance heater setup. There's 3B. Reset. Now we'll come back and run a recipe. Looks like it's already running anyway. Enable, set point. Now this, you can't see the PID values here. You have to come to this heater. So now 3B is running. Yeah.
Why the second temperature is still very low?
It's coming. So this is your ramp. Okay, so this is your set point climbing. So this is just an example of how you can watch something real time with the chart. You'll have to experiment with this because this part isn't in the manual. Now this will run that heater recipe up. And if there's any questions, you can just call in and say, hey, can you look at this?
What did you open this product there?
Down here. So you can watch it come up nicely. You can do it on an empty ampule. You can bring that heater over to the water ampule and just check it to make sure if you want to run the heater on the water ampule, not on the actual precursor, because you know in your mind how that graph should look. And you can run it like this. It takes a little over an hour to run it up nicely, but you can see how nice the chart is. And then you can take the data from that and you have the option to save. Well, actually, you can save it through here in different. You can add more parameters too. You can change the scaling on your axis. This is just something. It'd be good to come in and play a little bit. Yes. And you could do multiple charts if you want. So we're just gonna, I'm gonna do two things. Skip that. Then it goes to a steady state, which is the second part with the integral in there. Then it gives an hour for that. So I just stopped it and I'll come and turn that off. So that's how you would run an ampule heater. So now we're all done for the day or whatever. We're done with questions on this? Yes, sir. Okay, so how would you go about wrapping this up? Closing? Yeah.
Off all valves, off all heaters, zero all flows, and close the system. Can I go further?
Yeah. So you have to decide. We already closed the water valve. Is the water valve closed now? Okay. Make sure all precursors are closed. TMA we closed earlier. Now, what do you want to do with your bottled gas and your compressor?
Use that for this.
Compressor uses both? Okay. Oh, you just have to put this in. Okay.
So switch off the compressor.
Well, you're going to run it for over here. So, are you going to keep the bottles open or closed?
Yeah, I think the share.
So
Split,
oh,
split for both.
Good.
I think
Oh, you
that
bring it over.
side is split.
Okay, that's for you to decide how you want to do that. So you could, if you're done, you could shut off, close that valve and shut off the process pump.
close the software.
Or you can leave it open. You might as well close it because you're going to lose power. So this way you're courteous to the software. Close the software, shut down the computer.
Yeah, so that
So when we start this, we just plug in computer controls everything from I've got all the things.
Well, you'll turn, how are you gonna shut off the main breaker? Or are you gonna hit the E-stop?